scientific publication, high-ranked journals, which is the legacy of Professor Dinu. And he has, let's say, worked in 4 major and, let's say, 21 other international projects. He was basically the soul of many of the projects, although many times he did not lead the project. He was a modest person. But what he liked a lot was the interaction with people. Now, so this is about Professor Dinu, and it's, in his legacy, we would like to have we have a surprise for you. So basically, we will organize this fall another symposium, another workshop in the memory of Professor Dinu, which is the International Lithospheric Program Task Force 6 Sedimentary Basins. This workshop will be organized. Lăzărescu have agreed to organize this international workshop in the fall, and with this, Lucian is trying to get us the aula magna of the university in the Faculty of Law, and we will try to organize this workshop in October. It's a continuation of a long series of workshops, international workshops. We've been all over the world with this task force, and we'll try to bring this task force this year in October in Romania. Basically, and as always, this workshop is running always scientific volumes, and the current volume is basically a special issue of global and planetary change, which is a medium high impact factor journal. It's quite, and it's a result of the real non-result workshop which took place last year. Okay, and it's still open. Submission of publication is still open. So if any of you have a publication which fits this criteria, just let us know. And this is still open for submissions on first of all. I think this is from my part. I'm trying to be short, yes. So I'm a bit in time. So now we can start with the symposium. So basically the symposium organized by Ioan, mostly by Ioan, so we have to acknowledge Ioan to make a contribution. We'll have 4 sessions. The first session will be the taxi-heavy river system session. Okay, and this will be chaired by Professor Pani and by my colleague Andreas Kicker, the director of the Geophysics session. And then we have a session, second session for Top of Transylvania, which is a collaborative research project, and Mircea Radulian, who is the host of this collaborative research project this year, will chair this session. The third session is Geohazard and Hydrology, convened by Irina Dinu. And the last session is the session of basin analysis, which will take place later in the afternoon. And this will be convened by Marius and Marius Stoica and Marius Stilica, the 2 Marius of the basin analysis session. So this is from my side. Thank you very much, and I would like to hand over to the conveners of the first session.
So let me introduce the first person that will present the very important program, European program, Danubius RI, a pan-European initiative towards a distributed research infrastructure supporting interdisciplinary science in river sea systems. Adrian Stănică, the General Director of the Institute Geocomar, and also the, the heart of this program of Danubius RI. please. But just 15 minutes, it's very important.
Yeah, thank you very much. I don't know if I need a microphone. Sorry, yes? All right, no problem. Remembering Professor Dinu, I remember that once he said to me, when we were in the Delta on the houseboat, he said, Pongo is my nickname, as most of you know, you're a good guy, but your problem is when you say a secret, it's heard 2 kilometers upstream and downstream the Danube. So I generally don't need a microphone, but it's okay. I have no problem with that. For the online audiences, even though I had a career also in radio, and this is because I didn't need a microphone, really. That's a secret. So a brief introduction of the International Center for Advanced Studies on River Sea Systems, which has an abbreviation that generates misunderstandings and errors, Danube-RI. But it's not about the Danube. The idea was born in the Danube Delta and had Professor Panin and Professor Dinu in the center. So they are the initiators of this concept that we took over and developed over a bit more than 30 years now. So what is all about? The idea is to create a distributed facility that will support scientists from all over the world to deal with interdisciplinary science in river sea systems worldwide. Why do we need interdisciplinary science? Because going with the common concepts of science as we know them, with science silos as they have been so far, we have not yet found the solutions to the extreme events that are occurring. And this is why we need to find a proper understanding of how we can deal with the climate change scenarios, which seem to be worsening when we look at extreme events. We look at storms, floods, droughts, and all the multiple pressures coming also from the uncontrolled human development of the last 2 centuries. Not just that, we need to do something that science required for a long time. We need to develop a platform that will allow scientists to find solutions in a source-to-sink approach. And this is something that most of you know, the concept, the idea, but if we do not deal with river sea systems in a unitary way and with interdisciplinary science, we are not able to move forward, but I was able to move my microphone. So what we have been trying to do, just a second, because it seems that I played with my slides a bit. So what we are trying to do with Danube-RI, we try to develop an interdisciplinary distributed research infrastructure. Distributed means that it has components. It's like a puzzle spread in 11 European countries, and that bring together scientists from earth sciences, life sciences, social and economic sciences, trying to address the conflicts between societal demands, environmental changes, and environmental protection. What's unique for Danube-RI is that it tries to bring together communities specialized in freshwater basins, in freshwater science, with marine scientists, with a focus on the transitional environments, deltas, estuaries, and lagoons, which have been, surprisingly, mostly not focused on in the past 50 years, even though more than half of the global population lives there. So what is Danube-RI supposed to do? Besides bringing in earth sciences, life sciences, social and economic sciences, from freshwater to marine, spanning the catchment from source to coastal area, we try to offer a platform that will support innovative opportunities for boundary spanning. This is crucial if we want to move forward. We want to facilitate knowledge exchange. We try to create a new generation of scientists, and some of them are here in this very room, who started following this concept, the scientific concept, from source to sink. And since this has been a Romanian initiative, the hub, the headquarters of this infrastructure is going to be hosted by Romania in the Danube Delta with components all over Europe. So very briefly, as a scientific infrastructure, it's offering scientific services, which are the overarching challenges that Danubius-RI is trying to deal with. So it's the need to find solutions, as I said, to the mix of external and internal drivers. So climate change and extreme events, to the internal drivers coming from human activities, with three major focuses: water sufficiency, meaning quantity and quality; sediments and their management as the most neglected building blocks of our planet, actually, and the health of the ecosystem. Danubius-RI, as I said, is planned to be a puzzle, a distributed facility throughout Europe, with a hub in Romania, in the Danube Delta, and 4 major nodes. The nodes being components, facilities that support the integration of science in a way that follow the logic of knowledge, from data to information, from information to knowledge, and from knowledge to wisdom, finding solutions from impact. So it goes from the observation node that develops methods to integrate in situ measurements with Earth observation, satellite imagery solutions, with the data acquired going through a strict analysis process with the analysis node. Data that are collected and analyzed are conceptualized by integrating numerical models, trying to understand what's going on, and that's the modeling node. And the integration of the natural part with the social and economic part of the system, which is the impact node of Danubius-RI. These are the 4 nodes that are being developed under British for the observation node, German, the analysis node, Italian for the numerical modeling node, and Dutch for the impact node. And together we have been working to develop this infrastructure for about 10 years now. So since we are developing a research infrastructure, it does not provide only scientific services, but also educational services. And they are provided by the e-learning office through a Spanish compound that cooperates with a different ERIC, which is LifeWatch. And as I said, we support innovation, and the transfer of knowledge to business is coordinated by our Irish colleagues through the Technology Transfer Office. All this picture wouldn't be full if we don't speak about supersites. Danubius-RI is dedicated to provide scientific services at a global scale to river sea systems. But we need areas where we can test our ideas, where we can test our methodologies, our philosophy. It's areas of critical importance with critical pressures where we're trying to understand processes. These are called supersites, and at the time being, there are 10 supersites under development, from a Scottish loch as a Boreal transitional environment to the Thames estuary in the UK, on the Elbe estuary North Sea system in Germany, on the Middle Rhine and Rhine-Maas Delta, on the Rhine River in Germany and the Netherlands. Then in Spain, the coupled effect of 2 small deltas, Ebro and Llobregat, on the effect on the coastal zone, the Guadalquivir estuary, still in Spain, going to the study of the Po Delta and North Adriatic lagoons in Italy, the Nestos River Delta Sea system in Greece, which is a scale model, if you want, of a major river, and having the initial supersite in the Danube Delta that will be later introduced by Gigi. I don't know what happened here. I hope it doesn't move. No, it doesn't. So, as I said, supersites are the natural laboratories. So the idea is to find areas of critical, both natural, scientific, and human importance, trying to understand concepts for observation, research, modeling, and innovation. We chose our supersites not to duplicate the monitoring networks, but focusing, as I said, on critical parts, but trying to cover river sea systems as a whole, from the river source to transitional waters and coastal seas. And this is why you can see in the 10 supersites that are under development that we go from near pristine, like the Danube Delta, to the heavily impacted environment, like the Thames estuary that hosts London, which is the greatest human settlement in Europe. But again, Danubius-RI is not dedicated only to the supersites, but also to supporting research in other locations. So what we intend to do as a research infrastructure, we are not an institute. There were some misunderstandings around, unfortunately, mainly in Romania, that we would be duplicating the efforts of the institute. No, we are building facilities that are open to the researchers from the participant countries, but not only, for researchers worldwide. The policy of access is the open access policy, with scientific excellence and social and economic relevance being the main criteria. What has been important is the efforts that we started 5 years ago to develop a common set of standards for all the methods, going from sampling, data handling, data processing, data storage, going from earth sciences to life sciences. This is a huge amount of work, and we have been in process in doing this, but it's probably going to be a never-ending story, because the moment when we'll finish science, we'll upgrade methods, so we'll need to get back again. Again, we are offering free access to data for research purposes, supporting innovation with small fees to be charged, which is the normal thing for all the European research infrastructure consortia. And from the very beginning, we have been building our services to abide by the FAIR principles. FAIR principles of open data, meaning findable, accessible, interoperable, and reusable, which is the main concept to make our data more important. So, as I said, this is a Romanian idea, and the current effort started in 2010. But we need to go back to the early 1990s when Professor Panin started interacting also with Professor Dinu and persons from the European Commission and other scientists worldwide. We got on the S3 roadmap in 2016, and this was the first proposal developed by a country from New Europe, I wouldn't say Eastern Europeans, from New Europe to be accepted on the S3 roadmap. So we've been through the preparatory phase, preparing the documentation to become an international organization, which is going to be Danubius ERIC. ERIC means European Research Infrastructure Consortium, an international organization which will be hosted by Romania. And we have been in the process of creating the ERIC, with step 1 submitted 2 years ago, step 2, which means the letters of financial commitment from the countries, most probably going to be submitted to the Commission in December 2022. We're actually waiting for Germany and Netherlands, who gave us the dates of December 2022, when we should receive these letters of commitments for 20 years from Germany, 10 years from the Netherlands, respectively. And I won't enter into detail. It's been a hard work. It's been an enormous effort, but we are building this, and we hope to be operational by about 2024 to provide and test our services as early as next year, which is absolutely important. And we are not alone. In this, we have been working closely with other environmental research infrastructures within the ENVRI community. And most of you here are dealing with EPOS, and it's important to say that we have established a strong cooperation with the leadership of EPOS ERIC and also with colleagues in EPOS Romania community. And we have been growing, trying to fill in a landscape, trying to be operational, trying to provide excellence in a complicated environment. And we wish to go global, which is the final scope of this. And again, I have to say, had it been for Professor Panin here and Professor Dinu, who is not easy in our souls, we have never started this route. Thank you. And because Romania is contributing to Danubius RI with the hub in Muridiol, the heart, main laboratories, and with the Danube Delta Supersite, I will introduce our colleague Gigi Ungureanu to present this initiative of how to practically transform the Danube Delta into a living lab. Your Honor.
Thank you.
Okay. Okay, so good morning, everybody. I was brought into this whole idea of studying the Danube Delta and the coastline by Professor Dinu and by Professor Panin. So I'm in deep depth to them for the opportunity they offered to me during the years. And now I'm coordinating from J. Comar's part the efforts of implementing the Romanian components in Romania. I'm talking here about the Supersite and the geoscience component of the hub. And this presentation is about the two things, very, very short about the hub, but mostly about the Supersite and what we think we should build there and what we've planned to build there in the future. My presentation will comprise a few things about the hub and mostly details about the Supersite. What is the Supersite? Why Supersites are needed, but I will go very fast over this because already Adrian told you about that, many things. How will be the Danube Delta Supersite built, and what parameters will be measured in this facility, in this infrastructure. And also a few words about what we will offer to end users in the Supersite. And I want to, again, as Adrian said, to emphasize that we are not building an institute. We are not building a house for ourselves. We are building a hotel for others. So this infrastructure will be widely available to those who study river sea systems, including the Danube river system. These are the components that you've seen in the map before, and they were named by Adrian. The three red ones are the components located in Romania, the hub, the data center, and the Danube Delta Supersite. The hub will be located in Murigiol. There is a surface of 10 hectares which will be available. There is already a building there which will be integrated in the project that we are developing, and that has, the hub provides the management, coordination, and communication of the whole infrastructure, and also hosts a large number of laboratories, both of geoscience and earth sciences. So this wing is the geoscience, this is the earth science, and this is the aquatic ecosystem. This is an administrative building which will be modified. It won't look that fancy anymore in a fish shape from the satellite, so it won't be a landmark of Google Earth anymore, but doesn't matter. So what is the Supersite? The Supersite is a network of field stations and observation points that offer access to the whole Danube Delta Black Sea system, because it will extend from Galați, which is at kilometer 150 on the Danube, downstream to the Black Sea coastal zone. All the locations were selected with the aim to obtain scientific data and information that is necessary to the complex study, interdisciplinary and multidisciplinary, of the Danube River Black Sea system. And also in accordance with the Danube-Sarai scientific agenda. Each location has specific scientific objectives that I won't get into details now. There are many scientific challenges that the Danube Delta Supersite and all the other supersites try to address. First, as establishing the equilibrium between policies. Should we intervene? How much? Where? How? When? What is the impact? Is it better not to have an intervention? And everything has to be done in the mind that we already intervened a lot. So for example, in the case of the Danube Delta, not intervening means killing the system. We need to intervene to maintain the water, sediment, particle flow throughout the delta to the sea. If we don't do that, we will kill the delta. There is a need to find the compromise between environmental protection and the development of local communities. As my good friend says, in the Danube Delta, the most endangered species are people, because they are not allowed to do what they were doing. They are under very strict control, and in fact, the traditional way of living is completely under threat. And also, we need to find solutions to properly manage the delta ecosystems. Well, all these challenges require a thorough understanding of many things. But for one of the most important is how water, sediment, particle, and biota are changing in time and space in the system. So what is the dynamics of these components? What is the balance between natural and human-induced processes? And also, what are the social and economic dynamics of the local and neighboring communities? Because this is something very important about the Danube-Sarai. Danube-Sarai is not only about science. It's mostly about science, but not only about science. I mean hard environmental science. It's about the people, it's about the society that has to develop in a sustainable way, in accordance with what is happening and what has happened in these systems under the global threats such as climate change, development, and so on and so forth. So the Danube Delta Supersite has 7 field stations. These field stations are in Grindu, in Tulcea, now moved to Maliuc, Sulina, Sfântul Gheorghe, Murighiol, Sfântul Gheorghe, Sulina, that's Vuia Veche, and also Jurilovka. Each field station has under his supervision several observation points. These observation points can reach up to 9, such as for Murighiol station. But usually they are between 3 and 6. Altogether, we have 52 observation points. Out of them, 4 are coastal stations in the sea, 2 buoys in the coastal area near the shore, 6 boreholes, and 35 containers with sensors distributed all over the Danube Delta. And this scheme is the data transmission scheme in the Supersite. Everything is collected in the hub and then transmitted to the data center. So all the field stations offer a laboratory for sample preparation, preservation, and storage, both biological and for sediments, various field materials, access to waterfront and boats, means of transportation on land. There will be new buildings except one, which exists in Sulina, where there is already a stationery of the Romanian Academy that the Romanian Academy accepted to offer to Danubius as field station in the future. And these are some images of the places where we will build in Jurilovka, in Grindu, and in Chilia Veche. This is the building in Sulina, where we will have the Sulina field station, and in this place we see a sort of a headquarter of the Supersite to be located. Here, besides the laboratories of geology and biology, here in Sulina we will have also an analog modeling laboratory for geodynamics. So the field station will offer support to teams coming there to work, will administrate the observation points, will collect all the data from the sensors, and we will transmit this. They will supervise that everything is functioning correctly. They will do all the technical maintenance of the observation points. And the observation points, we have a few types. So we have land-based containers full of sensors, and we have also floating platforms. Most of them are of this type. So containers that will have about 29 sensors in it, in each container. That will be placed on floating platforms in various points, just to measure what we want to do. So we will have 2 buoys with sensors and a coastal station, the same type as GeoEcomar operates in front of Mangalia at 15-meter water depth. It's a mast which is articulated at the bottom to be wave resilient. In fact, 28 parameters will be measured online out of 130 parameters. Between these 130 parameters are a lot of biological and social parameters that will be obtained using periodical surveys, not online sensors, but altogether 35 categories of parameters in all these points. All the parameters were identified by Danubius, preparatory phase, the program Horizon project that defined Danubius RI. And in fact, there are several ways of determining these parameters: permanent sensors, offline, online, or gauges, repeated field measurements, indirect determination, for example, fluxes, laboratory analyses, and ecosystemic investigations with a variable frequency. These are some of the setups of sensors that we will use. The upper left image, for example, is from the Thames estuary, one of the observation points there. It's measuring chemical parameters of the water. part of the supersite, famed supersite. And these are the parameters. In air, water and sediment, chemistry and mineralogy, biology, social. And just to have a better image, all these parameters will be measured in several ways. You can see here the type of measurement and the frequency with color coded. And for each parameter, you can see there are several types of determination just to have a comparison and a double check on the data. And coming to the relationship with end users, most the main end users are the scientific and academic communities. But we think also of the local authorities, of administrations and institutions that sign cooperation protocols with Estuaries, for example, the Danube River Fluvial Administration or the National Protection Agency, companies, and we will offer a wide range of services to all of them. So what are the conclusions? 3, in my opinion. So building the supersite is a demanding endeavor. It's tremendous difficult, very complex task. But making a good use of what we build is even a greater challenge. So this cannot be done without collaboration. So window of collaboration is open, both to Romanian and international scientific and academic communities. So thank you very much.
Thank you very much. If there are questions related to Danube Sarai, we said that if there is any question, it should come now, both at the international organization Danube Sarai and what we are building.
If you have something to say it now or forever remain silent.
Since there is, we can just tell you that the Romanian component is going to cost about 120 million euros, and these are provided by structural funds, from the structural funds for research dedicated to Romania. And it has been a huge process. Probably all the documentation that is needed is half this room. I'm exaggerating. It's a quarter of this room. And probably 2 or 3 forests would have survived if things had been requested only in digital. But we are working hard. It's a tremendous work. And is fighting the Romanian bureaucracy is probably even more complicated than opening new ways in science. So thank you, Gigi. Now the next speaker, we're talking about the Danube River Delta coastal sea system in a unitary way. Our colleague Laura Butsu presenting the impact of meanders cutting the Lăzărescu branch on the local hydrologic regime. Thank you, Laura.
My name is Laura Butsu from Geology, and I'm very honored to be here to present you a study regarding the impact of the meanders cutting along the central branch on the hydrological regime. The area that we study is located on the Danube Delta, downstream of a large basin, the Danube Basin. Since the 16th century, people have been changing the natural course of the rivers in the Danube Basin, mainly for food defense, hydropower generation, and navigation. More than 4/5 of the Danube is regulated for Danube protection, while approximately 30% of its land is additionally impounded for hydropower generation. Over 700 dams have been built along the main tributary of the Danube, And the most important ones for the downstream area are iron gates 1 and 2, constructed in 1972 and 1984. The decrease of the sedimentary discharge has started before the construction of the dams, and we see here the data, the two set of data from two measurement stations, Orșova and Vaduoi, and we observe that the presence of the iron gates 1 and 2 hydropower dams has dramatically reduced the sedimentary discharge and the transit of the solid flows to the downstream. The Danube is the main contributor of fresh water and sediments to the Black Sea through the largest deltaic system in Europe, the Danube Delta. The Danube Delta has three main distributaries, Chilia, Sulina, and St. George. Our study area is situated on the St. George branch, which transports about 30% of the water discharge. The anthropic works in the Danube Delta started since the middle of the 19th century on the main distributary and on the interdistributary depressions, and the main works were meander belt cutoffs, construction of dikes, jetties, groins, construction of a very large network of canals, riverbank stabilization, and substitution of natural ecosystem into large polders. The St. George branch was in natural state until 1950, when the construction of dikes has started. Later, between 1981 and 1992, 6 free meanders of the St. George branch were rectified in order to improve navigation, diminishing the natural course by 32 kilometers. The artificial canals were initially constructed with 7-8 meters deep and with a maximum of 100 meter wide. The scope of our studies is to assess the impact of the cutoff works on the morphology and on the hydrosedimentological regime of the St. George branch, and of course, to estimate the effects of the distribution and water sediments fluxes in the entire delta. To answer these questions, we may use several methods, such as ADCP measurements, to assess the currents intensity distribution, discharges, multi-beam and single-beam data to make a bathymetrical map, and sediment and water analysis to calculate hydrodynamical parameters. Multiple sets of measurements were performed between 2006 and 2021 in the frame of many projects of GeoComar. We made several cross-sections, more than 55, distributed along all the branch, but focuses on the middle part of the branch where the rectified meanders are located. What processes follow the meanders cutoff? We found changes of the water flow and sediment fluxes, distribution between the former meanders and artificial canals. We found changes of the channel morphology and mobility, and changes in the water and sediment circulation in the entire delta territory, with effects on the Black Sea coast evolution. And if, regarding the water flow distribution, if we compare our data from 2021 with older data acquired just after the rectification works, we observe that just after the rectification works, the main water flow was transported by the former meanders, while now in 2021 the majority of the water flows from upstream are transported by the artificial canals. We have only a single exception, the second meander, the Dunavăs de Sus meander, which transport even now more than 70% of the water discharge. For the channel morphology, I will present you a survey, a bathymetrical survey on the bifurcation area of the Mahmudia meander, and we see that on the natural channel, sedimentation processes are dominant, while the artificial canal, A3, was intensively eroded. Going downstream, on the Dunavăs de Sus and Dunavăs de Jos meander, if we compare a shape, data from 1971, we observe that the second one, Dunavăs de Jos meander, is very, very sedimentation is the dominant processes. Regarding the artificial canals, I already said that the canals initially had approximately 7 meters deep and maximum 100 meter width. Our data show that now, in 2017, we found a depth of even 22 meters or 27. The width of the channel were also affected. We have two sets of data from 2000 and 2020, and we observe continuous decrease of the former meanders width and intensive sediment infilling of the channel by formation of large internal island. Regarding the sedimentary flows, higher concentration of suspended sediment are found in the main channel of the branch and in the artificial canals, which represent the main source of sediments. The low energy of the former meanders is observed also here. We see that the higher velocities are located on the artificial canal, while the former meander, the energy is greatly reduced. Which are the control factors influencing the distribution of the flow energy on the St. George branch? We found factors at local scale, such as hydrotechnical works, channel bed slope, band grain size, diversion angle, and so on, and at global scale, such as climatic changes and the human interventions in the entire basin. As conclusion, we expect a gradual clogging of the rectified meanders until their final separation, especially for Mahmudia meander, Dunavăs de Jos, and Dranov de Jos. The decrease of the sedimentary flow flows creates a sediment deficit for the coastal zone, and the changes in the distribution of the water and sediment fluxes between the distributary and the deltaic depressions have multiple effects on the biodiversity of the entire delta. As a perspective, it is necessary to establish complex long-term multidisciplinary research programs for understanding all the processes that control environmental changes in the context of continuous climate change and the increase of the anthropic activities. Thank you.
Well, thank you very much, Laura. If there are questions? Yes, one question.
Thanks for a very interesting presentation. Also very interesting from the perspective of what's going on in the Rhine-Meuse Delta in the Netherlands, where in the recent past we have also straightened our rivers. But today a major effort is going on to give the rivers back their space.
Yes.
And to create big also buffers to keep the water in the Netherlands, because we have major problems with floodings in the last few decades. And I wonder, let's say, whether this experience you have here has been also transferred to the people who do these engineering works in the Netherlands and vice versa. Because these are two of the major deltas in the Netherlands. And basically here, of course, for the program that you presented, of course, these are beautiful natural laboratories. So I wonder whether the knowledge from one system on Supersite has made it also to the other Supersite.
I know there was a PhD study thesis, Sebastian, which where the problems of the littoral zone especially were exposed, but I'm sure that there are other exchanges with the other locations where deltas where the problems are.
Because in the Netherlands, a major to restore things back, let's say, to conditions which were more natural.
But, and to add to what Laura said, we have been doing this study together. We've been working mainly for the past 15 years with Deltares, colleagues in Deltares, and we've been looking at nature-based solutions, going like this, how to use green protection against floods, looking at how and which should be the methodology to give space to the rivers, but also, again, using vegetation to decrease the floods, the velocity of the floods and the intensity of the floods, if you want. Here, on this direct aspect of cut meanders and hydrological changes, we have been working less with our Dutch colleagues, but it's more with British and French colleagues looking at this part, but it doesn't mean it won't happen. Because this is, what is here is a problem that challenges the concept of nature dealing with nature. For the Danube Delta Biosphere Reserve Administration, they took the policy of non-intervention, saying nature dealing with nature, starting 2003, around that year. So the situation is that they managed to almost kill the delta. Because as you have seen, if the meanders go to 20 meters water depth, there's no water going through the meanders, so all the water goes to the canals. No water in the meanders, so no more water with oxygen and water and oxygen exchanges with the interdistributary lakes and ponds and so on. So it means there's a widespread anoxia going all over. So now we are working together in finding solution in a series of projects.
Thanks. Thanks very much.
Liviu?
Quick question, what is the impact of an increased flow on the Central Georgia branch on the other branches?
The increase of the St. George branch
What is
discharge?
the impact of the increase in discharge in the St. George branch on the other branches?
I
That's
get-
a Dutch question. That's a good question.
I guess the deepening of in fact, the erosion of the artificial canals are an effect of the changing of the increase of the water discharge of the St. George branch. Less water on on other branches, and more energy on St. George branch, on the artificial canals.
Okay, thank you, Laura. Next presentation, our colleague in Geomar, Adriana Constantinescu. She will present Earth observation studies for water and sediment dynamics in the Danube Delta and northwestern Black Sea. Adriana, let's try to keep it concise.
I definitely need this.
I'm waiting for online.
Hello everyone, bună ziua. My name is Adriana Constantinescu. I was a student of this faculty doing my undergrad and my first master's here. And then I went on and specialized in marine geology. And what I'm going to present to you today is a small part of my PhD work. I was lucky enough to work and do my PhD in the Danube-Sarai community, and I'm probably the first PhD student to do a PhD using the ideas of Danube-Sarai. My work focused on the Danube Delta and the Black Sea area, looking at sediment fluxes. And today I'm going to show you how I used Earth observations to do that. So, studying transitional areas, it's quite challenging. And the Danube Black Sea area is no exception. So, looking at sediment fluxes, we basically chose two timescales that we were interested in. The decadal to centennial variations are studied through sediment coring, in situ measurements, hydrologic measurements usually, and hydrodynamic modeling. And then the seasonal to decadal variations can be studied with Earth observation satellite data, and of course validated and calibrated with in situ data. Now, using Earth observations for transitional waters, it's quite challenging. That's because transitional areas are extremely dynamic, so the processes vary in time and space. And also the algorithms that were available at the time, we're talking about 2015, 2016, were not necessarily suited for transitional areas, but I'm going to come back to that. Also, it's the difference of atmospheric conditions between the land and the sea. So the first thing that we did was to take hydrologic measurements and to plot water and suspended sediment discharge, and to see how these variations look on satellite data. So basically we chose 4 different moments, 2 of water and 2 of suspended sediment, a maximum and a minimum. And with the available satellite data that we had at the time, to see how the distribution of suspended sediment looks. Well, we actually used a parameter that is called total suspended matter. Now, this actually involves sediment, but it also It's basically everything that is in the water, it's floating in the water or is suspended in the water at a certain moment. So it's also sediment, but it can be organic matter, it can be phytoplankton, zooplankton, and so on. And we wanted to see how this looks in the Danube Delta and Black Sea area. And as you can see, we can have similar distributions of TSM if we look at water minimum and sediment minimum, but then it's really hard to tell what's going on in there. So basically what we did was to go forward, and in 2016 we had a cruise in the Black Sea, and we used the satellite data which was available at the time, coming from the Sentinel-3 also instrument, which belongs to the European Space Agency. You've probably heard of the Copernicus program, the program for the observation of the Earth. And Sentinel-3 is just one of the satellites which is dedicated to marine areas and coastal areas in particular. So the work that we did was concentrated around measuring in situ parameters such as total suspended sediment, total suspended matter, chlorophyll A, optical properties of the water. But during the cruise we also took the sediment course. And what I want to show you here, it's a transect that we did offshore the Sfântu Gheorghe mouth. And you see here a profile obtained from the satellite images. This is what we got. So these are the depth profiles of the in situ measured total suspended matter and inorganic suspended matter. And there are a few things about this. So first of all, they correspond very well to the variation that we see on the previous profile. Second of all, the value of 1 milligram per liter of total suspended matter corresponds to the minimum value of a river plume. So we can actually delineate the Danube plume using this parameter. What we see at the surface, it's basically only what it is at the surface. Going in depth, we see also the extension of the plume. So if you look at the blue and the red lines, you can see very well how the Danube plume extends at depth on a distance of 70 kilometers. This was part of my PhD, but I'm currently taking this work forward in my everyday work, and in several European projects, which are a contribution to the observation node of Danubius Arai. But this work is also a contribution to the development of the Danube Delta Supersite. So, one of the main challenges in the Danube Delta is its size and also its very dynamic nature. There are a lot of complex environments, large lagoons, shallow lakes, and so on, and also the anthropic activities and structures which change the sediment flux. For the Danube plume, it's not only the water and sediment discharge that controls its development, it's also wind, waves, currents, and so on. And a very big challenge in using satellite data for this area is the cloud cover, which is higher than other areas. And I'm going to show you just a few steps that we've been doing in the last 2 years in a project called CHORTO. It stands for Copernicus Evolution Research for Transitional Water Observation. Why this is important, it's actually particularly important for transitional areas. And that's because the Copernicus program has several services. One is dedicated to the marine areas, one is dedicated to the ocean, one is dedicated to land, there's none dedicated to transitional areas. And all these services have different approaches and they use different algorithms. So we want to harmonize these approaches and to find better algorithms that will be suited for transitional areas. And you see here the distribution of our study site around Europe. So there are two lagoons, the Ras Al Sinoa Lagoon, the Venice Lagoon, two estuaries, the Tamar in Portugal and the Plymouth Sound in the UK. There's also a lagoon, the Coronial Lagoon. And some of these sites are also supersites of Danube Sarai. So again, this contributes to develop Danube Sarai as well. And there's another project that we are also contributing to, Monocle. It stands for Multi-Scale Observation Network for Optical Monitoring of Coastal Water Lakes and Estuaries. This is kind of a different thing. We are actually developing cheap sensors to monitor water quality in this project, sorry. And I just want to present very briefly one of the breakthroughs of these projects, and it's about optical water types. So basically, an optical water type is a type of water that has certain values of remote sensing reflectance at a certain time. So basically, the same lake can have several optical water types, and we can, or the same lagoon, or the same, I don't know, river mouth, and so on. And we can associate them to sediment contribution, phytoplankton blooms, high bottom reflectance, if the lake is very shallow, for example, and the water is very clear, nutrient content, and so on. And we've identified so far 6 optical water types for the Danube Delta, and their distribution is in time and space is this one. And if we summarize, we can actually say which is the dominant optical water type at a certain moment. So looking at this map, it's quite easy to say that that class 3, for example, is more associated to sediment input than class 1. So these are just a few results. We're still working on this. We're doing a lot of in situ sampling at the moment, just to improve the algorithm and to, at some point, to be able to use this for other transitional areas. Thank you.
Okay, so
Questions? Oh, sorry.
Such a nice presentation escaped without questions.
yes.
How do you translate this quality of water types? This is very interesting. Your last slide, I think it's key in the presentation. How do you translate in terms of water circulation and sediment dynamics? Thank you. Just an example, if you can.
Can you repeat the question, sir?
How do you translate this quality of water in terms of these water types in terms of water quality and sediment dynamics, if possible? Can you make a direct relationship or not?
Yes, so first of all, we need to understand that we need in situ measurements as well. So I can show you something which is very interesting. It's the example of the Sinoa Lake. And it's actually, there's no algorithm that performs well in Sinoa, and there are several reasons for that. It's very shallow. Parts of it are silting, so they're clogging very rapidly. There's a lot of vegetation, macrophytes. There's a lot of resuspension because of its shallow nature. So it's important to know the source of the sediment, because it's probably the in situ sediment that's just being lifting from the bottom, basically, when there's strong wind. So knowing the natural condition is quite important. The reason we're doing this is because we need to be more confident in using satellite data for certain applications, and because they're so easy to use and they're so easy to download and they're so easy to represent, it's actually easier to see things which are happening suddenly. So very, very quick, very short processes. Have I answered your question? Thank you.
Thank you, Adriana. Final presentation of this session delivered by Irina Dinu, and it shows the application of numerical modeling on the Romanian coastal plain.
Well, hello again. I am going to show you quickly some of the things that we did in what concerns the numerical modeling applied in the Romanian coastal zone. A few things at the beginning. I mainly used two models. One model, SHIFEM, is developed by the modeling group from the Institute for Marine Sciences in Venice, and it's implemented on the Black Sea. And we studied it, we used it for studying the influence of the wind Danube discharge on the distribution of coastal currents. The developers have made an oceanographic forecast model by coupling SHIFEM with a wave model and with atmospheric circulation model. And I also applied it on the Sinoa lagoon system. Another model that I used in the coastal zone is SWAN, developed by Deltares. And it's a wave distribution model that we used for studying the effect of coastal protection solutions. Here you can see the map of the Black Sea, and the Black Sea grid actually is an early version of the grid. In the meantime, it became much more detailed around the Black Sea coast. You see an increased resolution in the Romanian coastal zone, but as I was saying, the updated grid has increased resolution all over the Black Sea. And it was possible because all these countries collaborated. Of course, it was before the war. There are boundary conditions on the rivers, the tributaries of the Black Sea. So is the Danube with the tributaries, is also the Dniestr, the Dnepr, and the South Bug. So I represented them because they also have an influence on our coast. And in the south, you can see the open sea condition on the Bosphorus Strait. Next. Oh, we're going. Okay. This is an example. So there were a lot of simulations. Some with real data, other with let's say more theoretical simulations in order to study the influence of various parameters such as the wind speed, the wind direction, the temperature and salinity that make the difference between a warm season and cold season. it's also the Danube discharge that is very important, because when it's high discharge, you can see a very strong current going southward, which exceeds the Cape Kaliakra in Bulgaria. This example is for a medium wind speed of 5 meters per second, wind coming from northeast, and with a medium Danube discharge of 6,500. It's just an example, as I say. This you can see the surface current in the to the left, and the current of 5 meters deep to the right, and of course the influence of the Danube happens all over the coast. When the discharge is higher, you can see a lot more red on the surface map, on the current map. Some cross sections through the model. You can see south of Sfântu Gheorghe. There. Oh, sorry. No, I don't know how to.
You need to insist. That's right.
Yeah.
No, but show it to the computer.
Sorry. Well, doesn't matter. Anyway, to the left, you can see the cross-section south of Sfântu Gheorghe. Up is the current cross-sections, down is the salinity cross-section, and to the left you can see the freshwater coming from the Danube. The same thing is cross-section south of Constanța, with which is the salinity distribution is more uniform. So, okay, and the same thing for the warm season. The difference is given by the temperature and salinity fields that are interpolated on the grid. They are climatological values. And here, the same thing, the cross sections for the warm season, and you can see the freshwater discharge is more extended in the summertime, and higher stratification. There were a lot of simulations made. I was a beginner in all this, but our collaborators from Venice also managed to validate the model based on a certain data set, an older data set, and they validated on temperature and salinity and water level values. One application of SciFEM is the Cassandra operational forecast model, where SciFEM is coupled with a wave model and a suite of meteorological models, providing real-time distribution of water level, currents, and waves. An example from Cassandra, I extracted the results from March 25. You can see the Romanian coastal zone, the water level, and the wave depth. Another application of SciFEM is on the Razelm-Sinoe lagoon. So this is the grid of Razelm-Sinoe. This is something that I'm very fond of because I made it. Is my only grid. Well, I made it with the help of some friends from Venice. Of course, I learned how to make a grid, basically, and we entered the discharge values on the junction with the Dunavăț, Mustaca, and Dranov channels. Sorry again. And here is an animation of the salinity. This is based on the there was a year of high discharge on the Dunavăț, Mustaca, and Dranov channels, and you can see how it changes all over the lagoon system. We needed, for this kind of simulation, we need daily values of wind, sea level, temperature, and salinity. The connection with the sea was by the Periboina and Edigiol inlets. In the meantime, I understand that they are closed, so everything changed. We calculated renewal times in several points all over the lagoon system. They are high, even in these conditions of high discharge. So it's an almost eutrophic environment. But for low discharge conditions, because we tried several simulations, you can see that renewal times are even longer. Well, I would like to leave the GIF going to the end. It doesn't take long. Okay, so there are many things that can be improved in what regards the modeling on the Black Sea and of the Razem-Sinoe Lagoon. So I look forward to more collaborations, and I really hope it is possible, because we have a project, and I hope it will have some more chances to work together with the team from ISMAR. Something else is related to the collaboration with the Laboratory of Marine Engineering in Barcelona. We use the model SWAN in order to estimate the impact of nature-based solutions. One of these issues is related to the presence of seagrass. We have an appropriate site, the Saturn, the beach between Venus and Saturn, where seagrass is a native species, and it's a Zostera noltei species, and it's currently regenerating. Well, it's been a recent interest in the seagrass in the last years, but usually they refer to it as a source of food and shelter for certain species. Together with the friends from Barcelona, we tried to assess its impact as a nature protection, as coastal protection solution, if possible. So we imagined that there would be seagrass meadow placed in front of the beach of the Venus-Saturn beach. We applied the SWAN model with and without vegetation. We compared the results, and we calculated the wave heights after crossing the vegetation meadow. Of course, referring only to the wave heights that from the directions that might have an impact on the coast. Our results show that the wave energy could be reduced, the higher reduction could be around 16%. So it is not spectacular, but this is normal, taking into account the characteristics of the seagrass at our latitude. So taking into account the height of the plant and the possible density. Another thing, sorry. Yeah, I know. Another thing, and I will finish with this, is related to another nature-based solution, placing artificial reefs along the Danube Delta coast. Well, we call them artificial reefs, but actually they are made of rocks, and they have a high impact in reducing the wave heights. We also use the SWAN model, and we compare the results for the waves after passing over the artificial reefs. We used extreme storms for the simulations, and we took them from a wave climate study carried out by a specialist from Hull-Crow, UK. And here you can see the proposed locations for the artificial reefs in north of Sfântu Gheorghe Maus and in Gura Portiței zone. We made several simulations with SWAN, first with the real bathymetry, and then with the modified bathymetry in order to imagine that we place there artificial reefs. We tried 2 locations at 5 meters deep and at 7 meters deep. And we used, as I was saying, we used extreme storms from wave modeling report. Because SWAN runs with the peak of the storm, so we needed pairs for significant wave height and associated wave period. We analyzed waves coming from northeast, east, south, and southeast sectors, which might have an impact on the coast. And we made a total number of more than 500 simulations, because we reproduced extreme storms with the periods of 1, 2, 5, 10, 20, 50, and 100 years. And we also consider sea level rise, gradually increasing the sea level from 0 to 1 meter. We looked at the output in a couple of points. Points from 10 to 12 are north of Sfântu Gheorghe Mau. Points from 23 to 26 are in the Zgura Portiței zone. And I can show you, we calculated the transmission coefficient, which is an indicator for the efficiency of an artificial reef. And I can show you a few graphs. We can see that for the zone located north of Sfântu Gheorghe, it is better to place the artificial reefs at 5 meters deep. So this is what we can say looking at these graphs. The same thing for Gura Portiței, where we can see that the artificial reef located at 7 meters deep is more efficient, because as you can see, the coefficient, the transmission coefficient is lower. And the analysis is ongoing, as well as all the modeling that we are looking to. So we are looking to get better forcing, both for the Black Sea coast and for the Razem-Sinoe Lagoon. And we are looking forward to the validation of the model. There are many things to say, but that's all for me. Thank you.
What's the structure of the artificial reefs you took into account? There are many construction ways, like they can be of metal, they can be of rocks, they can be of... How did you design them?
Rocks, I suppose. Actually, we talked about rocks. We didn't really talk about the artificial reefs. We only looked at the simulations. We didn't. I suppose that it's possible to reproduce them in the laboratory. I don't know. I was thinking about a laboratory. Yes, I think so. Yes, of course. I just looked in some literature, but to be honest, it's something that I still try to look for.
So, thank you very much, Irina. Are there any other questions? I have one question. Where is the coffee break area?
Before you go to coffee break, just a few announcements. Very happy. I guess everybody knows, but for the ones who don't know, I'm very happy to have today the family of Professor Dinu. So let me introduce to you the wife, Professor Dinu, Laura. The difficult part. fast. You have to take a coffee in exactly 22 minutes. So stand up sharply at 11 o'clock. The coffee room is the council room, 2 doors.
We start.
First presentation will be by Sir de Closing. It's about from deep earth to the surface, a tribute to Corneliu Dinu. Please, Sir.
Thank you very much. In the coming 15 minutes, in my tribute to Corneliu Dinu, I'd like to make with you a quick journey from the deep earth to the surface. And during this journey, of course, I have been inspired very much by Cornel. As mentioned by Liviu at the beginning of our meeting today, Cornel has left us with a very significant legacy. Our community at large, but also very much the community involved in the Romanian-Dutch cooperation. Cornel has served as promoter for quite a few PhD theses, starting with the PhD thesis of Liviu, but also the PhD thesis of Mihai Tarpanca, who is here also today, and Ion Menteanu, one of the organizers, the key organizer of today's meeting. Very characteristic for Cornel was also his very unselfish collaboration in getting other PhD theses realized in the context of our joint efforts in this beautiful system, the Carpathians and surrounding parts of this dynamic piece of the Earth. It was really a journey that is going on till today, and I'm very happy that today many young researchers are continuing to work in the spirit of Cornel. And as mentioned by Liviu, his spirit was very high. He was a happy man, and he contributed to happiness of many people around him. These are some pictures of Cornel as a promoter and member of PhD committees in the Netherlands. And again, we are missing him. That's very clear. But I'm very happy that so many people are here today at this meeting as a tribute to him. Cornel was very much thinking on different scales in time and space. And in that spirit, I like to start off by showing you a picture of the mega plume in the northern Atlantic, detected by tomography, a mega plume system with high temperatures in the upper mantle at levels that already start, let's say, at shallow depths, but levels that go down all the way to the core mantle boundary. What is also very interesting in this system are the side lobes of the Iceland plume, including a side lobe that goes all the way to southern Norway, where we have mountains far away from the plate boundaries. Always has been an enigma. Now we know it has something to do with a hot upper mantle. In the coming minutes, I will focus a little bit on the interaction between these plumes and the overlying lithosphere. I will start off with the mode of penetration of the plume inside the lithosphere, making its way to the surface. But at the end of this presentation, I will also say a few words of the downtrusting of the mantle part of the lithosphere on the side of the plume, which is actually providing us with a overlooked mechanism for the initiation of subduction. What is very interesting, of course, is the realization that although plumes in oceanic lithosphere are always associated with a large-scale uplift, a swell in the lithosphere, this is not the case for the plume lithosphere interactions when the plume is attacking a continental lithosphere. In that case, lower crustal flow is initiated, and the surface topography is not a continuous swell, but it is a set of depressions and highs. These plume lithosphere interactions have also significant impact on rifted continental margins. And these margin systems have been studied intensively, also because they are often associated with major hydrocarbon reserves. But what is a very interesting observation, that half of them are associated with underplating and with sieve dipping reflectors, having a very nice expression of the magmatic processes which are going on during rifting and afterwards. The initial concepts about the formation of rifted margins were very much in terms of end-member models. Active rifting associated with plumes, and what is called passive rifting, which is basically attributed just to the action of plate tectonic forces. Well, what is very interesting, if you look a little bit closer and you also learn from thermomechanical modeling, then you realize that these are indeed end members, and that between them we have a semi-active mode and a semi-passive mode. And if you go to the southern Atlantic, then basically you see expressions of all these different modes of rifting. Let me first bring you to the southern Atlantic, the southernmost part, the Argentina rifted margin, which is a classic case for active rifting. The plume makes it all the way into the lithosphere, is providing sieve dipping reflectors, and very dramatic underplating. If we go a little bit more to the north, to the northern Brazilian margin, we see exactly the opposite, passive rifting. So no plume penetration inside the lithosphere. If we go, however, a little bit more down, in the area between southern Argentina and the northernmost margin of Brazil, then we have a beautiful case of semi-passive rifting. Underplating, but not a dramatic expression of the magmatic activity close to the surface. So this has led us to a new classification, basically filling in the gap between passive rifting and active rifting for large-scale plume lithosphere interactions. Let me go down now a little bit in scale, and let me go to the secondary plumes, which are originating from the mantle transition zone at a depth of 400 kilometers. For that purpose, we have focused on two areas, basically two different settings. The European Cenozoic rift system, associated with very small scale plumes, also called baby plumes, and Eastern Asia, in particularly China, and the Baikal Rift, where we are basically having a mixture of interplate settings, but also back arc settings. Let me give you some examples of what tomography has learned us in the last few years. Very nice expression of small-scale plumes in the, for example, the Eifel region, but also in the Massif Central. And in the Baikal Rift, similar thing. And then we go to Eastern Asia, and there you see on the lowermost panel on the right-hand side in the paper by Xia, you see basically a deep-seated plume coming up all the way from the deep mantle. But by the moment it is hitting the mantle transition zone, you see the creation of three secondary plumes. The area of Eastern Asia is also interesting in the terms of the providing us some very nice back arc settings, where you see plumes arising all the way up from the stagnant position of the down-thrusted slab. So we have them in different sizes. And also the mode of penetration is different. It varies from finger-shaped to arrowhead and to basically mushroom shape type of interaction with the overlying lithosphere. In order to explore that, we have recently carried out a modeling study, and this is joint work with Alexander Koptev, presently in Potsdam, and also Istvan Kovac from Budapest and Chopron, and also involving my co-worker Fred Beekman and Alessio Lavezia, currently with INGV in Bari. The model is shown here. We start with a small plume at a depth of around 400 kilometers. We have a lithosphere, an overlying lithosphere, which includes a weakness zone, and we follow basically the path of the plume all the way to the surface, taking also into account the effect of a hydrous plume. So instead of only looking at thermal plumes, we were inspired very much by Istvan to take into account the notion that quite a lot of evidence has been accumulated in the petrological community, proving that plumes in many cases, especially the small ones, have a hydrous nature. What is very interesting, if we play with that, and if we play with the density difference between the rising plume and the surrounding mantle, and we take into account that the hydrous plume has a higher density difference with the surrounding upper mantle, that we can also partly explain the differences in the near surface expression in terms of plume lithosphere penetration. It looks like that this finger-shaped penetration, which you see in the right-hand column, is optimally created by a hydrous plume. That means a high density difference with the surrounding upper mantle, in particularly also if we put a lithosphere under some external extension. And that basically leads us to better insights in the different expressions of these baby plumes. The Eiffel area is a typical example of penetration with a finger-shaped mode. That's the panel in the middle. If you go basically to the case at the bottom, you see also a finger-shaped mode, but you are already in the late stage of the interaction of the plume and the overlying lithosphere, which is also leading to downtrusting of the surrounding mantle. And that is a very interesting situation, because that's a process that we are also seeing in other settings, such as the Caucasus, but also in the setting of Iberia, where we see areas where we have a hot upper mantle, an uprising plume, essentially flanked by areas where we see downtrusting of mantle lithosphere. And when you see in this panel red color, it means a plume type of rise. And when you see blue or green, you see downtrusting of the surrounding lithosphere. So these processes are coupled. And that's something that we have not realized in the past. Here you see the situation for oceanic lithosphere. Plume is going upward. By the moment it starts to interact with the overlying lithosphere, you see in the right-hand panel, you see downtrusting of the surrounding mantle lithosphere. And that's basically what we need, of course, to get initiation of subduction. Of course, the common wisdom is initiation of subduction is primarily a process of getting oceanic type of lithosphere back into the mantle. That was also the topic of my own PhD, by now quite a few years ago, 40 years ago. But now we also realize that initiation of subduction can also occur in a continental setting. And that's basically what you see here in this panel from a paper that we published a year ago in G-Cubed, where you see different simulations for different ages of the overlying continental lithosphere, and where you see in purple the downtrusting of the mantle part, and where you see in orange and yellow the work of the plume. And what is interesting, if you look to the different ages, then you realize for a young continental lithosphere, this process doesn't work that well. It's simply too warm, it's too light to really get down to deeper levels. And you see also that for a very old continental lithosphere with an age of 1,000 million years, basically it also doesn't work that well, because that lithosphere is simply too strong to get mechanically decoupled. Optimal ages are in between. In particular, let's say the age of 150 million years is a very good one for this process. Well, these are concepts. The key point is, of course, to collect data. And seismic tomography has made a wonderful job in the last decades. We have a lot of advances in analytical studies, and to bring it together, of course, is a major effort requiring teamwork. In that context, I'm very happy with the efforts of the community in this part of the world to realize an ADRIA array project, covering the whole system in this part of the world, with major implications for better understanding of the type of processes which I have been discussing in my presentation. The same is true also for the Topo Transylvania project. And also in that project, basically Cornel was involved. He came to our meeting in Brasov, organized a few years ago. He's standing here on the picture with a group of researchers, also including here the chair, the convener of this session. Liviu was also there, and you can also see from the picture on the side that he was actively engaged in the discussions we had at this meeting. So I think it's very fitting that we are here with Topo Transylvania at this meeting. And again, it has been a privilege to have also there Cornel with us. So let me end up with a very brief discussion. Connecting the deep earth to the surface remains challenging. It will keep quite a few people off the street also in the coming decades. It has kept me off the street also for quite a long time. Multi-scale Plume lithosphere interactions can lead to a wide spectrum of tectonic expressions at the surface. And in the spirit of Corneliu Dinu, new observations and international projects such as Adria Array and Topo Transylvania hold the key. I'd like to leave it here. Thanks for your attention.
Thank you, sir. There are questions or comments? If not, let's go to the next presentation, which will be done by Istvan Kovacs. It's about integrated geodynamic station and the Paragazosphere Hypothesis.
Ladies and gentlemen, it's a great pleasure to be here with a small Hungarian delegation. And I also have a personal account about Professor Dinu, because I was lucky to meet him in person exactly 20 years ago at an IGCP meeting in Vietnam, and I could witness his warm personality and also his scientific excellence. So we are also paying tribute to his scientific and personal legacy with this talk. And who we are. So we are from the Institute of Earth Physics and Space Science. And this is a new institution in Hungary, or let's say a new independent institution, which was born exactly 1 year ago. So we are celebrating its first anniversary. And first I would like to tell you a few words about what we are doing and who we are. And after we will jump straight into the global plate tectonism and some aspects, and after we will focus a little bit on the integrated geodynamic station. The Institute is responsible for space science, which means that we are basically observing the near Earth space from geomagnetism and also the ionosphere, and what is around the Earth, space weather forecasting. And we are also constructing now a zero-magnetic laboratory, which is a very interesting building where the Earth's magnetic field is reduced to zero inside in a cube. It means that we can carry out different experiments, biological, engineering, and also earth science experiments. And if all goes well, this new building will be handed over somewhere during the summer. So I hope we can share you more about this. This nice building here is the recently renovated headquarters of our institute in Sopron. And we also have a geodynamic observatory in Sopron, or close to Sopron, where we are recording the stresses and also the deformation of the lithosphere due to tidal forces and stresses. And of course, last but not least, our institute is responsible for actually operating the Hungarian seismological network. And this network has been expanded dramatically in the past, let's say, 5 years, because before that we had only 10 broadband seismological stations, but due to the Alpere initiative and also the PACES initiative on the eastern part of the country, we managed to install 30 new stations. And also, as Sird already pointed out, we are actively involved in a Adria Array initiative, and we put our broadband stations into operation 2 years ago, so we are sort of already participating in this. And we do hope that it's a big opportunity for Eastern Europe, and it's really a historical moment when we have the opportunity to learn a lot of new things about the lithosphere under this part of Europe. Okay, and that was a very ugly word at the beginning, Paragazosphere. So what the hell is the Paragazosphere, or why are we talking about this? So the thing is that the lithosphere-asthenosphere boundary is, of course, an important boundary in the Earth's interior. However, even after more than 50 years of the modern plate tectonic theory, there is no compromise in the pathological and geochemical community what this boundary means. We know, of course, from the work of Sird that, of course, it's an isotherm, so it's a thermal boundary. But what happens at that particular temperature, nobody exactly knows. And also, in the past, let's say, 2 decades, there are emerging geophysical data that besides the lithosphere-asthenosphere boundary, we have another very important discontinuity in the continental lithospheric mantle. And this is called the Mid Lithospheric Discontinuity, which was observed under cold and old continental plates. And this boundary lies more or less around 90-100 kilometer depth. So we can say that these are 2 important prominent boundaries which divides the Earth's rigid outer shell from the less viscous and probably partially molten interior. And here we provide, let's say, a simple model both for the lithosphere-asthenosphere boundary and also for the mid-lithospheric discontinuity. Because if we are looking at regions which are characterized by high heat flow, such as oceanic, young oceanic basins, and also extensional basins like the Pannonian Basin, where the heat flow is high, then we believe that the Pargasite dehydration solidus here, so what is the Pargasite dehydration solidus? Basically, we have different minerals in the upper mantle, and the most important factor controlling the melting temperature of the upper mantle is water and volatiles. And we looked into the experimental work and found out that even if we have very small amount of volatiles, especially water, in the upper mantle, then the melting temperature of the upper mantle is around 1100 degrees. So, okay, what happens here, let's say in shallow depth? So the melting temperature of the upper mantle is exactly along this line, and the pressure doesn't really have an impact on that. So it means that if the temperature is high, we have partial melt on this side, and the other side we don't have partial melt. So we think that the lithosphere-asthenosphere boundary from petrological point of view is a temperature at which the upper mantle starts melting, okay? And we think that the lithosphere-asthenosphere boundary in young extensional basins and also oceans coincides with this isotherm, so the 1100 degrees isotherm. However, if we looked at places, and another extreme, the cratonic and Proterozoic continental areas where the heat flow is low, we observe the middle lithospheric discontinuities around 100 kilometer depth, and this coincides very nicely with the pressure where this hydrous mineral breaks down and releases a lot of excess fluids. And on the top of that, we can also do, let's say, pathological models for these different scenarios. First, have a look at the scenario when we have the high heat flow, like relatively high heat flow, like oceanic areas or young continental basins. And of course, as I told you, the water plays a very important role. That's why it's indicated separately. And you can see that the quantities are absolutely low. So we are not talking about a lot of water there, like in subduction zone, but very tiny amount given in ppm, which is a very, very small amount of water. And also here, you don't have to worry about the mineral names. I don't want to scare you with this. So this is the composition of the upper mantle. We also add water. We define the different minerals and the fluids. And from these model, we can forecast the electrical resistivity and also the seismic speed, how large is the propagation of the seismic speeds. And from that model, we clearly see that there is a large drop in electrical resistivity and also the seismic speed at the LAB. And if we move on and we go to the other extreme, the cratonic and proterozoic areas, you see that we still see something happening around the Mid Lithospheric Discontinuity, which more or less the same what we observed in high heat flow areas, the difference being that after this decrease, this sudden drop, it goes back to a more or less continuous trend. So this is basically the Paragazosphere hypothesis, and it's all about water. But there is, of course, not only water, we know very well, there are other important volatiles like the carbon dioxide in the upper mantle. And here you can see that we have nice fluid inclusions in upper mantle xenoliths from the Pershine volcanic field. And these tiny little inclusions inside the rocks are filled with carbon dioxide dominated fluids. So the carbon dioxide and another important player in this game, and we shouldn't forget about this. We also shouldn't forget about fluid inclusions. Okay, and why can we use the Paragazosphere hypothesis in this context? Well, the reason is, if we have an extensional basin like this, and of course we have an elevated lithosphere-astenosphere boundary, an astenosphere, what happens is that after the extension, this astenospheric dome starts cooling. And what happens during the cooling? The partial melt, which is in the astenosphere, starts crystallizing. But the carbon dioxide-rich fluids, of course, cannot stay in the minerals because carbon cannot be incorporated in the mineral structure. Therefore, it will form a separate fluid phase. But of course, carbon dioxide doesn't like to stay in the upper mantle. It would like to escape. And of course, it moves gradually towards the surface, as you see here. And of course, what drives this process, this propagation of these fluids from the elevated astenosphere towards the surface, is the stress, which is accumulated within the lithosphere and also in the crust, so in the shallower levels. So this motivated us to come up with the idea of the integrated geodynamic station. And what is special about this, that we are doing simultaneous observation of the seismic activity in the Earth's lithosphere. And the most important thing is that we are also measuring the gases coming from the deep. And if we have this continuous time series of each of these components, then our hope or theory that we may be able to detect signals which basically precede earthquakes. And this was put forward in a nice recent Alexandru Sakac. And of course, we put that into the operation. Originally, it was meant to be in the Carpathian Band area, but because of the COVID disease, the field work was quite limited, so we had to change our mind, and we installed that in the Bakony-Balaton Highland area. And you see, the area where we actually installed the station is close to very deep faults, cross-cutting probably the entire crust, but maybe also the lithospheric mantle. So we have the deep fluids coming towards the surface. And that's how it looks like. It's like a little small box. And what is this here? So it's an infrared spectrometer. So we use an infrared spectrometer to measure the composition and also the concentration of gases coming out from the soil. And we can make analysis in every 5 minutes. So you can imagine that with this special instrument, we are able to analyze simultaneously the atmospheric carbon dioxide concentration and also the carbon dioxide and other gas composition coming from the Earth's interior. And with this, we can produce a very huge number of infrared spectra. And of course, we can have a very detailed time series of the carbon dioxide composition as a function of time. And this is a special occasion because this is the first time when we present these results at an international conference. And you know, this was all achieved with the help of Romanian colleagues and also colleagues from the Netherlands. So we are really proud of this, that it's, let's say, is the first real kind of achievement or product of this collaboration, of course, besides the papers that we published so far. And okay, so this is the carbon dioxide concentration here. This is the time, of course. And these green stars here indicate small earthquakes happening in the vicinity. So in the vicinity, I mean in the, let's say, 50, 60 kilometers neighborhood of the integrated geodynamic station. And the interesting thing is this event here, and I highlighted this because this was the biggest earthquake, but probably you were laughing at me. In Hungary, a magnitude 2 earthquake is a big one, because fortunately we don't have big earthquakes, so if we have a magnitude 2 or 3 earthquake, it's already something, and we are happy with it. And it's very strange, or I don't know, it's strange or it's just a coincidence, but we do observe a small increase in the gas concentration just prior this earthquake, what happens. But of course, at the time being, I wouldn't like to read too much into this because it's only a very small time interval, and probably we'll need at least 2 or 3 years of time series and also bigger earthquakes in the region to be conclusive whether there is really a relationship between the increased flux of volatiles coming from the deep earth and the seismic activity or the stress accumulated in the lithosphere. But I think at least these results are encouraging, and we are now having even 6 months data, so we will see how it goes. And also we are very happy that we learned last year that we have the funds to build a second station in the Carpathian Band area, so we will also monitor the gas fluxes there, and also with the help of the NIP and colleagues here, we hope that we may come up with some interesting results. Okay, and it's just to finish with a very happy crowd. A few years ago, with great hospitality and great time in science, probably you recognize some familiar faces here. And also, I'm sending the best wishes our director, Viktor Westergom, and Csaba Szabó, who unfortunately couldn't make it in person. So thank you very much for your attention, and it's our pleasure to be here.
Question: what is the depth of collecting CO2?
Sorry, what?
Depth of collecting CO2.
Oh, okay. So the probe that we use is done at around 1 meter, more or less. Yeah.
Some kind of rock.
Yeah. We are also observing, I didn't mention that because there was only a short time allocated for the talk. We are also measuring the meteorological parameters. And of course, we are also paying attention that the variation that we see, of course, from one point of view is meteorological and it's controlled by the change of pressure, but we can account for that. Yeah. Thanks.
Yeah, my name is Spider from University of Budapest. I had two, but let's get one at least. Thank you. In your model, you have water, CO2 at 100 kilometer depth. What is the physical state of these at 100 kilometer?
Thank you very much for the question. So basically, at such a high pressure, the hydrogen is incorporated into the mineral structure in mineral defects, so like vacancies. So it's not water, in fact, but structural hydroxyl. These are, we called them the nominally anhydrous minerals. But also we have hydrous minerals like the amphibole or the phlogopite. So we can also incorporate the water in these phases. And in addition, if the temperature is high, of course, we have melt. We may have silicate melt or carbonate melt, which can, again, incorporate water and carbon dioxide as well. The carbon dioxide is usually present in this, as we just showed in this image, in these fluid inclusions. Marty can tell a lot of things about this. I'm not an expert in this domain. And also it can be present in let's say, silicic magmas dissolved, and also it can produce carbonatitic magmas as well.
We go to the first next presentation is by myself. It's about earthquake properties in the Vrancea seismogenic zone. Just a few words, because now we are in this symposium in memoriam of Corneliu Dinu, and just a few short words about this occasion. There is a saying in Romania that when you speak about the people passed on, you have to speak of well. Don't remember anything bad they made in their life. As concerned Corneliu Dinu, it's one of the few persons in my life that I really don't find bad things. So it's not a problem for me to speak about well, because I keep in my memory only nice things. He was so nice person, and it was a model for me as scientific researcher and also a human being. Okay, so just a moment. Is here a problem? Okay. Yes. Oh, please. Maybe I made a wrong here. Is not work. Okay. But yes, the presentation is okay. Oh, okay. Let's go in this. But it stopped. Why? I have to go this way. Okay. So I focus in my presentation about only a few things about Vrancea earthquakes, because there is quite a large subject and the time is not so much for the presentation. It's about non-symmetric seismicity patterns in the Vrancea, depth variation of seismicity and specific mechanisms, volumetric component that can be a component in case of Vrancea earthquakes, and attenuation. Finally, some conclusions. So, Vrancea earthquakes, they have some interesting geometrical configuration about large Vrancea focal mechanism, because you have this orientation of the fault plane, which is practically in the same direction. And also, if you look to the radiation of seismic waves to the surface and the effects of these events, they show the same asymmetry. Maybe people of Romania know very well that this is the case for 1977 earthquake, and the effects of these events are focused on this direction, and damage was important in this direction, even at large distance from the epicenters. At the same time, you have a strong attenuation if you go to the Transylvania, which is also characteristic for the Vrancea earthquakes. Now, if you go to the depth variation seismicity, Vrancea is a particular case because all the earthquakes in the mantle are concentrated in a spatial volume, in a specific volume, which is well defined, and it's almost vertical going to the mantle. At the same time, there is a sort of deficit of seismicity between the crust and the subcrustal regime. And if you look more carefully for this, for example, for this profile, you can see that the crustal activity is somehow, it's apparently going in the same direction to the subcrustal earthquakes. Here you see that speaking about intermediate depth events, we can speak about two segments in Vrancea. These two segments, one around 100 kilometers, the other one around 140 kilometers. I noted them A and B. If you look to the seismic activity in time, in the upper segment, when you have for this time interval, you have two big events in 1977 and 1990. You see there is a sort of background activity which is almost constant, and you have an increased activity caused by aftershocks in 1977 and 1990. If you go at the same time, if you look to the second, the bottom segment, segment B, you see that the background activity is almost constant as in the A segment. There is nothing here. When 1977 earthquakes occurred in the upper segment, there is nothing perturbation in the lower segment. At the same time, when you have 1986 event in the B segment, there is nothing happening here. It's like that these two segments are somehow decoupled from seismic point of view, but probably not only seismic point of view. And if you look here to the background activity, it's in a large image. We draw up the aftershock activity. You see that the activity is almost constant for the two segments, but there is a scale between them. I mean, the number of earthquakes, the average number of earthquakes in the B segment, it's about 5 times larger than in the A segment. Now it's another image. This is the distribution of the number of earthquakes with depths. You see two maxima corresponding to these two segments. And here are the aftershocks for the 1977, 1990 for the segment A and the 1986 for the segment B. You can see the aftershocks are practically limited. They are practically blocked. So you have no aftershock. After 1986, there is no aftershock going in this segment and vice versa. It's like that in this depth domain, there is a sort of process, neurological process, which seems to act on the seismic generation of earthquakes. It's like we wondered some time ago if there is a very resistant material, or by contrary, if it's a low resistant. Okay. And it's a big question if this segment can be ruptured in the future. I think that we are going to understand little by little what is happening here. So now, Ivan already presented you about the Paragazosphere modeling and hypothesis. So I'll try to pass a little bit fast. The problem is that due to this this component in the mantle, which are create the possibility to have fluids, to have water, and also carbonate, and also, as Istvan showed already, that there is around 100 kilometer depths. There is a sort of critical situation in depths. I mean, in these depths, we can have suddenly an abundance of fluid. It's important that this mid lithospheric discontinuity is located roughly at the same depths when we have this problem, this change in branch activity generation, which is very, very possible to be related to this mid lithospheric discontinuity. Okay. We know already that discontinuity means some weakness, means fluid presence, means resistivity decrease, increase, electricity increase. So it's apparently it's a band when the seismicity has a particular geological background to be generated. Okay. So also, as I showed you already, that there is this specific generation of earthquakes in the upper and lower segment in the Vrancea, with, for example, for 1977 and 1990, the rupture propagation was upwards. So starting from somewhere here and going this way, nothing in this direction. If you go to 1986, the rupture was downwards and nothing to the upper part. We can suppose this is something to be understand in the future. We suppose that there is different physical processes generating earthquakes in the upper segment, in the lower segment, and this probably is due to fluid presence and also maybe some phase transformation if you go to the downwards branch. Okay. This is a representation of frequency magnitude distribution on depths. Very briefly, there is this minimum here, close to 90 kilometers, and then decrease in this deeper part. These two decrease means that probably there is higher stress in these regions, and we have, for these two parts, we have generating big earthquakes, which is not the case around 100 kilometers and 130 kilometers maybe. Okay. If you look to this distribution of big events, these are events of magnitude above 4.8 in the Vrancea, and you have to, these are focal mechanisms, and if you look to this profile from southeast to northwest, it looks like there is some weakness planes generating big earthquakes, which are also some decoupled between them around some depths. Okay? These are just a few aspects to understand a little bit what is happening in Vrancea. Now, if you have fluid presence, then we have to look for volumetric component in the focal mechanisms. For the moment, there is nothing very clear in this way. This is due from different reasons, including errors which are inherent in this kind of inversions. But for the near future, it will be, in my opinion, important to look to this volumetric component because this is evidence of fluids in generating earthquakes. Okay. Now there is some performant inversion algorithms like INPAR by Vasile et al., which can separate quite well this volumetric component from the double coupled components. And just to, I saw review coming, I have to finish. This is a slide about attenuation. You know that going to the northwest, we have attenuation. And if there is some, in this figure, you can see that we have some inflow. If you have some inflow of asthenospheric in this part, you'll have different paths going from focus to the surface, and they can explain difference in the attenuation, even if the two stations are quite close in space. I mean, about 50, 70 kilometers. Okay. Okay, as I told you, the seismicity pattern in Vrancea is not uniform. This can be due to fluid presence in this part, not only in Vrancea, but in particular for Vrancea seems to be very important. And this can be related to the presence of this mid lithospheric discontinuity, we can look for volumetric component in the source. And also, it's possible to imagine a scenario for delamination, because in that, if you have fluids, you have oceanic lithosphere. And it's possible that along the horizon, corresponding to mid lithospheric discontinuity, it's possible to have this delamination in Vrancea. And then you can explain several features related to the Vrancea seismicity particularly. Thank you very much. If there are questions, yes, Sird.
Thanks a lot for a very interesting presentation. It is gas in the seismicity levels of around 40 kilometers. Has that been observed in other downloads?
Yes, it was observed also in Hindu Kush. It's something similar, not completely, but it's quite similar. And also, I think it was also observed in other slabs. Yeah, in Caucasus, I think also. In Pacific, yes. So it's not very specific for Vrancea.
Let's say Caucasus and in the Kush, typical examples, let's say, where we subduct the sphere, which is not entirely oceanic, also
continental. Yes, but it looks like it looks like this mid lithospheric discontinuity is also observed in continental active region. We have compression. Okay, other question? If not, let's go to the next. Yes.
I wanted to capitalize on I'm sitting closer, but it may not be question I have one. What do you mean if by any means we are saying that the Vrancea seismicity is not part of the Arctic subduction? What other possibilities exist to explain Vrancea?
So there are different models in this problem. Okay, one of the assumptions we can consider is that we have an oceanic subduction from Eastern Europe, from Mysia, and then in time there is followed by a continental collision. This is one of the main model, but.
For the effect of the subduction process.
Delamination, yeah, okay. You have first subduction, and then it's delamination. And okay, there are many aspects in this. Yes, it's difficult. Okay, let's go to the next presentation by Alexandru Sakac. It's about gas emanation in the target area and their applications to the project, to the top.
Okay, hello everybody. I am giving this talk on behalf of my major co-author of this presentation, Csaba Szabó, who cannot be here for health reasons, and also on behalf of my colleagues in the Topo Transylvania project. You can see the long list of people here. Please note how long the list is, how many people involved here. And with bold, I emphasized those people who are specifically involved in what the title shows. So the gas emanations. I am starting with a picture exactly the same with which Sird Kluting finished his talk, intending that to show you that Professor Dinu was among us in one of the Topo Transylvania meetings, namely in 2016. And the merit of being with us, it was Sird's, because he was who had the excellent idea to invite Professor Dinu to this meeting. So we benefited from his deep insight and his advices. He was supporting us, fully supporting our project, and he contributed to our meeting. You also can see the number of people here in this picture. Only one missing. Who made the picture? No, I'm there. Okay, just compare with the long list report. It means that during the last 6 years, okay, our team was growing significantly with eminent scientists and older generations who were attracted to the project and involved fully. So this may give you a glimpse of how this project is going on or is developing. This is a session about Topo Transylvania. This is the name of the session, Topo Transylvania session. But nobody introduced the Topo Transylvania project. So Topo Transylvania is a project. We started informally, then growth and became more and more formal, more and more people involved. So the purpose of my talk is to place the subject, the gas emanations, in the larger context of this project, of the Topo Transylvania project. So the major goal is that we want to understand the complex processes, geodynamic processes, which are active now, ongoing, in the Carpathian Band area. Why just here? There are a number of reasons why we wanted to focus on this area. Okay? So this is almost, I think all of us know, that this is the most geodynamically active area in the Carpathian Pannon region and one of the most active in the whole Europe. And it hosts a large variety of geodynamic processes which are concentrated and focused in time and space toward this area, the Carpathian Band, including volcanism, migrating from west to east, dynamic topography, evolution of the Transylvanian basin itself, okay? Volcanism, post-volcanic activity, geothermal anomalies are there, okay? Seismicity, which are other than Vrancea seismicity, okay? So in this relatively small area, a lot of ongoing geodynamic processes are working now. Okay. Other reason is that this area is just very close to Vrancea. Vrancea seismic area, just across the Carpathians, 40 kilometers or less, even less. And finally, the reason is that till now, it was not a coherent geodynamic explanation or a model which encompass all these kinds of processes, including those from the outside of the Carpathian Band to the inside of the Carpathian Band. So this is our target area, mostly focused at the interior of the Carpathian Band area. This is why the name Topo Transylvania. Okay, let's have a look what kind of methodology we use to study this area. We already have seen the goal, which is the main goal. Also, we have some implicit targets as well, which will be evident toward the end of the talk. Okay? So we use a complex multidisciplinary investigation, combining a number of geological and geophysical tools and methods, disciplines, each of them representing a module in the project. And each module in the project has a team, its own team. That doesn't mean that one person in the project cannot be part of different modules. Okay? So let's enumerate those. We have petrographic, geochemical, and volcanological studies, okay, to focus on the most recent volcanism in the whole Carpathian Pannonian area, which is just here. The Persian Mountains, with last volcanism more or less about 500,000 years ago, and Csomadul volcano, which is less than 30,000 years ago, with its last eruption. Okay. Also, we target mantle materials, xenoliths coming up with the Persian volcanic, in the Persian volcanic area, okay, just to study the mantle properties and compositions at the time when they were incorporated in the basaltic magma. Also, we use space geodesy using the INSAR methodology to monitor topographic changes, even at the level of millimeter per year topographic changes. So now we have capabilities to do that. The picture in the right-hand side is showing a so-called corner reflector, which was developed in Sopron with some original conception, which reflects the radar signal coming from the satellites. Also, seismology, monitoring local seismicity other than Vrancea in the Carpathian Band interior, magnetotelluric studies to find out properties and heterogeneities in the lithospheric mantle and even in the astronosphere, and which is emphasized, which is the subject of this presentation, fluid studies. So we have two kinds of fluids to be studied in our project. One is the fluid hosted in minerals as inclusions, or hosted in minerals in the form of in the mineral lattice, as in nominally anhydrous minerals such as olivine, such as olivine, pyroxene, and feldspars. Okay, and the second type is gas emanation. So with this, I come back to what Sird's Kluting's title, from deep earth to the surface. So what else is more representative than fluids originating in the deep earth and coming to the surface? Okay. So the journey about what Sird was talking about is the journey also of the gas coming up from the deep earth, from the mantle to the surface. And we are trying to monitor and understand the gases sampled at the surface. And also the materials containing the fluids in the rocks, as I told before. Okay, and we want to do this with international and interinstitutional cooperation. At this time, we have 3 countries, 6 institutions, and a lot of people involved. So the fluids to this module of the Topo Transylvania project, okay, we want to understand the origin, composition, migration paths, and time series variation of those deep originated fluids. This module has 2 panels. Okay. One is the study of the fluids trapped in the mineral, as I told before, and the other one, which is emphasized, the study of surface gas emanation of deep origin. And this is the team, the people who was emphasized as both in the first slide involved. Okay. So now we restrain the talk to these, the study of surface gas emanations of deep origin. So this has the main goal to see how different parameters of the surface arriving gas, mainly carbon dioxide, such as concentration, flux composition, varies in time, and which are the factors controlling this time variation of those parameters. So we have 2 methods applied to this. One is a continuous monitoring of both diffuse emanation of carbon dioxide, and when we can. Just before coming here to the conference with the team, we were in Covasna and sampled gases and waters for this occasional monitoring, non-systematic monitoring, to analyze the gases, compositions, even isotopic compositions, and so on. So we have to go back 50 years ago when Professor Irene did a pioneering work. This is a quite forgotten person, a geophysicist, who had this brilliant idea to monitor MOFETs, not the concentration, but the level, which is proportional to the flux of the gas in different models. And he arrived to the conclusion that besides the atmospheric pressure, there are internal causes which determine modulation of the CO2 emanation in different ways. He named those variations in analogy to the surface geophysics anomalies, time anomalies of the emanations. So this is a picture you already have seen from István. This is the complex gas monitoring station, which, okay. Can I go back? Okay. So what we do is to monitor. We get access, unrestricted access to a MOFET, which is not at all used. So we have it for any time for our scientific purpose. Okay, this is the interior of the MOFET pool as seen in infrared, and with our monitoring equipment there, which is recording CO2 concentration across the whole depth of the MOFET with 20, and also atmospheric pressure there. These rough data are not processed and are not interpreted yet. Okay, we wait for longer time series, and we were not correlate with earthquake activity yet. Okay, related to the CO2, the origins, there are different studies, which is more or less common. These people acknowledge that at least part of the CO2 comes from the mantle. Okay. But still the paradigm of volcanism. And okay, this is the last, almost the last slide, invoking this Paragazosphere hypothesis and the paper of it, and you already have seen this picture, okay, explained by István Kovács, and you will, okay, you just imagine in the lower right panel that thing there is Vrancsa. This is a conceptual model, but it was with Vrancsa in mind devised, okay, and then you have the fluid generation and the fluid upwelling. So this is why we think Vrancsa deserves to be monitored via fluid properties, exactly what we are doing with these two types of gas monitoring systems. And I finish with other picture of Professor Dinu, exactly what Liviu said at the beginning of his friendly mood, always positive, and I am proud to share at least one occasion in the Topo Transylvania project with him. Thank you.
Și pointerul aici. Următorul buton, pointerul și stâng jos, stângă de microfon. Da. Și microfonul să înmânăm.
Mersi. Hi everyone, my name is Laura Petrescu. I'm from the National Institute of Earth Physics in Romania. And I will be talking to you about the role of fluid embrittlement in Vrancsa earthquakes. perspectives from, so how we can approach it from the viewpoint of stress inversions. So as you probably all know, Vrancea is a big seismic enigma. It hosts the largest terrain-releasing seismic nest in continental Europe. Earthquakes are distributed in this really narrow, almost vertical volume, up down to 200 kilometers, and its origin is highly debated. On the right here, you have a distribution of seismicity, and this is a tomography from Ren et al. 2012, showing that the seismicity here is actually just like on top of the limb of on top of an high seismic anomaly iceberg, if you may. It's not the right word, but still, of downwelling cold materials that go down to maybe the mantle transition zone. So the Vrancea is anomalous because it's actually located far away from any active plate boundaries and it's offset from the actual Miocene suture, which is known in Romania to be the suture between Precambrian terrains and incoming accreted European terrains. Earthquakes occur at depth where, and this is the most important, deformation should be ductile, so we do not expect seismicity to occur there due to the pressure and temperature conditions. It has the brittle failure is not possible without some assistance. And also it underlies the Meusian platform, whose basement is actually of Precambrian age. So the top of the Meusian platform is covered, as you all know, in Paleozoic and Neogene sediments, but the crust is actually a Precambrian in age. And the whole seismicity underlines this crust. So what are the actual possible mechanisms for earthquake generation at these depths where you do not expect seismicity to happen, where brittle failure is not theoretically possible? There are three main generational models. They are described here very well in this image, which I stole from an EGU blog. The first one, which I'm also actually going to concentrate in this presentation, is called dehydration embrittlement. So when hydrated minerals, they expel water, fluid, like actual fluid water inside the pores of the rocks, the pressure, the pore fluid pressure increases, which has the ability to weaken the rock, and which triggers rock embrittlement. This is essentially, it's a very simplified version of it. The second one, it's called thermal runaway. So basically, if a rock is deforming in a shear sense, there's heat being generated along the line, and the rock becomes unstable and again prone to brittle failure. And the third one, transformational faulting. This is a very popular generational mechanism, especially for really deep earthquakes, like even 600 kilometers deep earthquakes. Basically, minerals undergo phase transformation, so they rearrange their atomic structure, resulting in this fine-grained rock that is easier to deform. So again, we are going to focus on dehydration embrittlement and how that might be able to explain Vrancea earthquakes. So the possible actual mechanism, the real-life example for this to happen is how you need to introduce fluids and volatiles in the mantle. And in the case of a subducting slab, fluid can be, water can enter the oceanic lithosphere, especially along the bending folds and all these reworked transfer folds, and it's captured inside the minerals. When the slab enters subduction, it's subject to high pressure temperatures, which causes dehydration, and of course melting, volcanism, and the whole classical subduction system. If we can demonstrate that there are fluids in Vrancea, that the embrittlement is assisted by fluids, this would imply that Vrancea is of oceanic origin, unless there is some other process that might be able to explain the water being there, or other types of volatiles. These are some of the most famous geodynamic scenarios for the existence of our infamous Vrancea slab. There's the oceanic slab subduction and progressive breakoff. There's oceanic slab subduction and progressive tear. There's the Rayleigh-Taylor instability or lithospheric drip proposed by Lawrence and Hausmann in 2009. The lithospheric delamination, so just like scraping off part of the lower continental lithosphere and foundering it into the mantle, or the unstable triple junction scenario. However, each one of these scenarios has a problem. Especially the delamination one. And Dan McKenzie, they published a paper in 2020 showing this is showing the distribution of earthquakes inside the oceanic lithosphere that is progressively, so this is age here, so the oceanic lithosphere, as it ages, it becomes increasingly thicker. And the lines show the temperature distribution. And you can see how all earthquakes, these are just different types of earthquakes, strike slip, thrust fold, normal fold, they all occur above the 600 degrees temperature Celsius. Also, there's a paper in 2021 or 22, I might have mistaken the year, but Ferrand and Mana, they modeled the thermodynamic stability limits for minerals that are typical of uppermost mantle. And they found a very good correlation between Vrancea earthquakes and the dehydration of antigarite. So this mineral is usually associated with serpentine that's found on top of the subducted oceanic slabs. And also here, I don't know if you can see in the back, but there are some the word is slipping. The isotherms, yeah, that's the word. The 800 degrees isotherms and almost 900 degrees, there are earthquakes occurring at temperature, pressure conditions they should not be occurring at. So again, one of the most viable explanations would be the dehydration of typical oceanic lithosphere minerals. So how can we approach this from a stress ratio perspective? What is the relative stress ratio? Basically, in an isotropic medium, with round pores, the pore fluid pressure acts the same in all directions. Changing the pore fluid pressure would produce no change in the relative magnitudes of the sigma 1, sigma 2, sigma 3. So these are the three principal stress axes of the stress tensor. If the medium is anisotropic, such as the fractured, faulted oceanic slabs, then changing the pore fluid pressure results in a asymmetric poroelastic response in these three principal stress axes. So this was shown in laboratory experiments. The stress ratio, or sometimes it's called the shape ratio, stress shape, there are various names for it, is this big R here. It's basically the ratio between sigma 1 minus sigma 2 over sigma 1 minus sigma 3. Typically, what it shows is if R is low, that's generally associated with extension. If R is high, it's generally associated with compression. You can see here some of the scenarios for compression, strike slip, extension, and the distribution and the relative magnitude of the different stress axes. Change, okay. So it's been shown that increasing the pore fluid pressure, this reduces the normal effective stress. So the this is shifting the Mohr circle towards this failure, the Coulomb failure envelope. What this means exactly is that the orientation of faults is broadening, and that satisfies the reactivation criteria. So a wider range of fault orientations become susceptible to slip. There are two papers that I found associating this change in the stress ratio with fluid pressure deformational instabilities. So there's one from 2016 where Martinez Garçon studied pressure changes inside the geyser field. So they showed, actually didn't show the other picture, but there's a correlation between the change in the stress shape ratio and the inferred injection rates in that geyser field. And another really cool one is a 2019 paper from Japan, where they saw a correlation between slow sleep events and, again, the change in this stress ratio derived from the focal mechanisms from earthquakes following the slow sleep event. So how do we estimate R? At the surface, usually stress can be measured using various geological observations, also paleostress for that reason, but at depth, we have no actual direct way to look at stress. So what we do is we invert the focal mechanisms of earthquakes. This is again all the earthquake parameters, mechanisms in Vrancea, down to 200 kilometers. And they can be clustered and inverted to estimate the directions of the principal stress axis, as well as this relative stress ratio. So what I did was divide this 3D volume into an regular grid of overlapping cubic cells and take all the mechanisms available from the National Institute for Earth Physics catalog. It's called ROM+. Oh no, actually that's for all the earthquakes. We have another catalog for earthquake focal mechanisms. So these are all the earthquake focal mechanisms since 1940s. So I divided this volume into a regular grid and then inverted each grid cluster into the directions of sigma 1, sigma 2, sigma 3, and R, using this really cool MATLAB software, which is open source and can be downloaded for free. These are the results. Basically, each globe here signifies the directions of the principal stress axis and the confidence intervals for each axis direction. So again, I'm not estimating the actual magnitude, just the directions. From this plot alone, we can immediately recognize that the stress is dominated by vertical and well-constrained sigma 3, and a horizontal sigma 1 without a preferred orientation. And vertical extension is predominant. And one of the coolest results I unexpectedly obtained, and this actually triggered me to understand what R can signify and how it can be used to understand whether fluids are present in Vrancea or not, was this shape ratio image, where I divided my inversions into earthquake magnitudes. So this is the inversion for the magnitudes for the earthquake magnitudes less than 4, showing stress ratios below maybe 0.6, 0.5. But earthquakes that are higher in magnitude, they show really, really low stress ratios. That's a really interesting and unexpected result. So I didn't know what this meant. And then I started, Google scholaring and trying to find papers to understand why this dichotomy appears in my results. So again, this R negatively correlates with changes in pore fluid pressure. Again, an increase in pore fluid pressure can arise from slab dehydration, which enables brittle failure. And I interpreted this change, this disparity, as a suggestion, maybe more of a speculation, but it seems that small earthquakes are more clearly associated with preferential elongation of the slab, while higher magnitude earthquakes could be generated by other mechanisms, such as dehydration embrittlement, which ultimately would imply that Vrancea is oceanic in origin. I leave you with my conclusions. So we used earthquake source mechanisms to estimate this reduced stress tensor. We showed that vertical tension governs the stress field in this descending lithospheric body. The relative stress ratio changes may be used as an indicator for changes in pore fluid pressure. And there's a striking decrease in stress ratio with earthquake magnitude. So again, fluids in Vrancea, I don't know, maybe. Thank you.
Thank you. If there are questions, Siert?
Thank you.
Back to the figure of Mackenzie.
Yes. That was among the first ones, I think. Yeah, this one.
Basically, this is a result that we already know nearly 40 years due to Wittgenstein.
Yeah.
Made a point that the depth of earthquakes in the oceanic lithosphere is systematically increasing with age. But none of them goes below an isotherm of 600 degrees, which at the time they presented that basically was fully consistent with the strain growth calculated on the base of dry olivine rheology. If you do the same trick for a wet olivine rheology, the strain would be gone already at depth levels of, let's say, 400 degrees. So how can you explain this pattern by the moment you start to play with a wet rheology? Because it looks a little bit a paradox. You favor an oceanic slab to basically get this pattern that you recognize in Francia. But if you go to the interplay settings in the oceans, it comes just the opposite.
So you said if you include a wet mineral in the simulation, you get earthquakes only below 400 degrees Celsius.
You lose the strength of the lithosphere already at shallow levels.
Okay, yeah.
And let's say this is what Wittgenstein came with, but let's say in order to explain the earthquakes then at the deeper levels, they basically propose this the ductile faulting or something like that.
Ductile faulting, yeah.
So the point was, let's say, that the actual mechanism of the stress release could be a different one of the actual mechanism to build up strength in the lithosphere. That was the point.
Yeah, yeah. Sorry, there was a question or?
Well, I'd like to mention that this is an old problem.
Yeah.
But Mackenzie was certainly not the first to do it.
Yeah, yeah. No, he reiterated this decades-long problem. But the thing that we want to extract from this plot was that even if you delaminate lower crustal regions, which are aseismic in the first place, you won't get seismicity at depth. So this doesn't explain delamination. This contradicts the delamination hypothesis. That's why I put this plot here. But yeah, we should talk more about the other simulations, and I'd love to work with geodynamicists on this and try to understand my results more. Thank you.
There are, I think, a lot of things to discuss, yes, for the future. Next presentation is by Thomas Lang. No? Oh, I don't know. It's some change? Okay, so it's Thomas Lange about upper mental fluids and their role in earthquakes and generation emanations. I realized that a lot of talks were go around the fluid presence, which for me is clear that it's an impact of Topo Transylvania project. You see already.
Okay, thank you very much. It's really an honor to be here. So you have heard a lot of presentations about fluids, about earthquakes, and also about deep processes, and also that there is possibly a connection between the deep and the surface. And in my presentation, I will try to connect these topics in a way that I try to combine geochemical, geological, and geophysical results from the literature, and also that I show you now here, which we have acquired just a few months ago. So when we talk about deep fluids, we always ask ourselves, what means deep? Well, when we define it as fluids originating from the lower crust and the upper mantle. And if it's coming from a deep and it's traveling to the surface, then we again ask ourselves, does the fluid's composition change? Volcanic areas. So just to give some additional information, in the Carpathian Pannonian region, we have a few places where we have deep faults. And for instance, in the northeastern part of Slovenia, we have there fluids coming to the surface that have literally the composition of fluids which we can also find in the Earth's mantle. We heard that CO2 is a very important gas, so we will also focus on this. But besides CO2, we will also focus on noble gases, primarily on helium, because these are inert gases, and if they migrate, they won't change in their composition in a way that what we call fractionation in chemistry. They will mix. So but still, after mixing, we can predict a source region for these gases. As I mentioned earlier, and we have also heard about this, that deep fluids can rise to the surface through magmatism or spontaneously with the help of deep-seated faults. We will concentrate on non-magmatic fluids. These are dominantly metamorphic of origin, so we exclude also in organic CO2. And now we will go to the Carpathian Band. We have heard a lot about the Carpathian Band in the previous presentation, so I don't want to go into the details here. But it's very important that our study area is the city Covasna, which is situated at the boundary of an intermountain basin. And of course, we have there thin-skin trusting, so we have there the Audia and the Tarko naps. So this is very important for us for this location. And CO2 in this region is presumably non-magmatic. We will talk about this in a few slides. And of course, the CO2 is coming to the surface, or we can measure the CO2 in springs where it's associated with water. And we have also MOFETs where we have just pure CO2, what we can directly measure. So the city Covasna, you can see it here on a Google Map image. We have three places what we have sampled. One of the localities, the Hanko Valley, is very interesting for us because we have there a fault mapped by geologists, and we have here several springs which can be found close or along the fault itself. And what is very important that on every location we collected water samples and also in situ gases from the water itself, so that means that they are dissolved and are in equilibrium with the water. So they have a joint history, and here we have the isotopes what we measured. So I will show results from these isotopes. So here are some images from the sampling. We have taps where we collected the gas. These are taps that bring water and gas from more than 100 meters to the surface. And we have also former baths where we see water and also bubbling inside the water. So we measured the area of the bath where we have the bubbling itself. And for instance, which is very interesting, that we had also a spring which was next to the river, and although it was very close to each other, there was a huge difference in the chemical content of the two waters, for instance, pH. So this means that we were very sure that during this sampling we can dominantly exclude the water what we have next to it. So it's very, very complex, and also in the city we have more than 20 locations where we can sample CO2 in the future. We just focus now on these few locations because we were interested if we can trace some deep origin of the CO2 in the waters. And what you can see here is a diagram of what we got from the isotopic values from the water, so the hydrogen and oxygen. And I don't want to go into the detail. What I just want to emphasize here is that we have a so-called mixing line between the local meteoritic waters, which means that it's groundwater, so from the surface, and we have an area which is defined for metamorphic H2O, which means that H2O released during a dehydration of a metamorphic rock. And what we can see is that in the Henkel Valley, we have samples that shows that the water before mixing had a metamorphic origin. If we look at the result of the dissolved gases, we see that we can make a diagram from with the help of noble gases and the isotopic ratio of carbon from the CO2. And again, not going into the detail, what I want to say about this is that we are on a mixing line of the mantle and limestone. Why is this important? Because we are very close to the mantle endpoint. And what we always look at is that we have a number which is above 1, so this means that there's an enrichment in the lighter helium. This is very important to emphasize because this means that the contribution of the mantle, we know that there's a contribution of the mantle to the gases, but we see also that we have limestone that contributes to our gases, which means that when we look at the source of these gases, then we need a kind of decarbonization of limestones, which are not stable in the mantle beneath the Carpathian bands, so as far as we know, and thus have to come from the Earth's crust. So we can presume that we have a hybrid fluid which is coming to the surface. So when we try to interpret the results, so to understand what their evolution is and where they originate from, so I used the cross section of Tilitsa and al. And what is very important that we have here, of course, an asthenospheric uplift, and beneath the Eastern Carpathians, we have here a heat anomaly, which for us is very interesting because it means that here, after cooling, it starts to heat up again, and we see that these 1,000 temperature degrees goes into the lower crust. So we will focus now on this crust and mantle boundary, and besides the crust and mantle boundary, we will also look into two other sections to understand the migration of the fluid. So it was told earlier, so you have heard earlier in the presentations that CO2 in the mantle doesn't like to interact with the minerals of the mantle and will spontaneously degas. And what we see here that we have faults cross-cutting the whole crust. And we have also mantle rocks from the Persian mountains, which are ultramyelonitic mantle rocks. So we expect that these weakening zones continue in the Earth's mantle. And why is this important? Because in experimental geology geochemical works, it has been emphasized that these weakening zones help fluid to migrate faster than normally in the lithospheric mantle. Yeah. So what is very important so we know that at least we expect CO2 to come from the mantle in this form. What is also important that, of course, we saw that the temperature is increasing here in the lower crust, and we have here, and as you have heard earlier, presumably carbonate and also mica, so hydrous minerals. And due to the increasing of temperature, these minerals will destabilize and release CO2 and H2O. So that means that we can connect a metamorphic process to the CO2 and H2O. But of course, following the next question is, how can CO2, or at least not the CO2 but the fluid itself, migrate through the crust? There's a work made by Sleep and Blampide from '92 who modeled the connection between earthquakes, stress, and fluid migration. And what they said is that when you have a pressure on the weakening zone, then the weakening zone itself will release the fluids, and after you can't put any more pressure on the weakening zone, and there will be a movement. You will generate a lot of, well, you can say, pores in this weakening zone. So the fluid will go back into the weakening zone itself, but not in the same direction. But it will have a small angle, and that's why you will have not a continuous migration of the fluids, but it's an episodically story. Why is this important? Because it means that the faster the movement along these weakening zones, the more fluids can migrate to the surface. So that's why it can also be for us a conclusion why we have a lot of non-magmatic fluids emanating at the surface. Of course, when we continue on with the weakening zones, we know that in the upper crustal region, NAP boundaries and also faults, like for instance faults found at the boundary of the intramountain basins, can help fluids to migrate, and then of course emanate, for instance, like at Covasna. So just to sum up my presentation, what I want to highlight is that it is we need a lot of results to find a connection between the deep and the surface. And although with geochemistry, we get a source for these gases, these fluids, we of course need a joint, so we need a cooperation with geophysicists to understand what happens in the deep, and in that way we can better understand what is happening and how we can later on use these fluids, so benefit from them, like for instance what you've heard, connections with the earthquakes. So with this, I would like to thank you for your kind attention.
There are questions? Yes.
From mantle is one of the, let's say, the reason for some of the hypogenes spirogenesis, if you are aware about this. I mean, the dissolution of limestone by basinal fluids coming up from Srimantat or from Jatasun. So, is there in Covasna area any cave or testimony of a cave which has been generated by hypogenes spirogenesis?
I don't know any kind of cave there in the...
Sorry?
As far as I know, there is no cave around Covasna.
Okay, thank you. I mean, this hypogenes spirogenesis
I'm sorry, we don't have time for extended discussions. So
sorry?
We're very late. I will have to stop.
Wow, that's not nice.
Okay, otherwise you will not eat.
To the next presentation by Felix Borleanu. It's about preliminary results of attenuation tomography in the Carpathian-Pannonian area revealed by ambient seismic noise analysis.
Hello everyone. First of all, I'm grateful to be here to this nice meeting in the memory of Professor Dinu. In the following slides, I'm going to show you some new insights about the attenuation in the Carpato-Pannonian region from the seismic noise analysis. This study is a part of a larger project, exploration projects that aims to image the lithospheric structure in the East European area using noise processing, seismic noise processing. So the objectives of this study are to compute the Kodak quality factors of the Rayleigh waves obtained from the correlation of the noise, and to see how are the effects of the structures upon the modulation of the waves amplitudes. And also to map the attenuation structures in this area. These are the data that we have used. You may notice the high density station coverage, and we used two different time periods. The station that operated in this area between 2007 and 2011, and also the ones that operated in 2020. You may see that the race coverage is very strong. So to obtain the virtual earthquakes, the cross correlation between the noise signals, we started from the daily recordings. We removed the instrument response, and after that we filtered and removed the trend and the mean, and applied the continuous wavelet transform in order to remove the transient signals as earthquakes or anthropic noise. And finally, we cut the seismogram segments of 4 hours and cross-correlate them, obtaining the so-called virtual earthquakes. The point is that to obtain these signals with a high signal-to-noise ratio, we have to correlate as much as possible data, and you can see here the two cross-correlograms filtered in short periods in the long periods range, and the part from the left, it's also called the acausal part, while the part from the right is called causal part. And you notice that the signal-to-noise ratio increased with the amount of the data analyzed. Here we show an example of cross-correlation obtained for Muntele Roșu recordings. These are the examples of correlation obtained in short period range, and you may notice that some influences of the noise on the microseismic noise, while for the lower period range disappear. So this is we processing the coda waves in 4 different period ranges, and these are the comparison between the virtual earthquake computed between the correlation of the signals recorded by the Amara station in Romania and an Ukraine station. And you see that there are huge similarities with a real earthquake. And we use to determine the attenuation, the coda quality factors, the coda signals, which are strongly incoherent in comparison with the P waves. This is the flowchart of the computation algorithm, and it's important to notice that we can obtain the attenuation images through regionalizations, and also by directly from the inversion, by computing the coda sensitivity kernels as forward modeling. And this is the envelope of these signals when filtered between 5 and 10 seconds in black, and in red is shown the smooth signals, and this is the envelope decay. And these are the time limits for the coda windows, and this is the Rayleigh wave arrival. We may notice that this analysis is strongly influenced by the coda windows that we have to take care in order to not have influence from the distance range and also from the length of the coda time window. In generally, the coda quality factors depends on the scattering and absorption measurements, but in the diffusive regime, these depends only the absorption. Here we measure the coda quality factors for several distance ranges, and we may notice that they have an increasing trend with the distance, and therefore we had to limit our measurements in this time window, in this distance range between 50 and 250 kilometers. We plotted here the quality factor distributions, and we remove from the analysis the tail of these measurements. And here are the histograms of the correlation function of the back azimuth and the interstation distance. And we notice that the azimuthal coverage is rather good, while the distance we notice that are better covered for the station at larger distances. We performed the Sikhanov inversion, and we compute the damping parameter from the L curve in order to not underfit or overfit these values, and also the obtained images. And we compute the resolution of our analysis using the checkerboard test. And we've seen that the input model, it's well recovered in all the periods or in all the selected period ranges. Here we show the CODA quality variation obtained by dividing the inverse quality factor of its average, and in red are shown the regions with high attenuation, while the blue color show the low attenuation, Ionian Basin and Bohemian Massif. These are also related to the sedimentary area, and also correlated with the tectonically active regions. Here we computed the CODA quality factors for each station, and by computing the mean of the values acquired for each station. And we low CODA quality factors, which means high attenuation, are shown in red, and high CODA quality factors in blue, which means low attenuation. We've seen that the trend is also kept in the medium and large periods intervals, excepting probably in this long period range where we have less measurements because the decreasing of increasing of scattering in the results, and we eliminate the measurements with the standard deviation higher than double. We've seen that our measurements are not biased.
What we have to do is provide a sort, let's say, an input geometry for the model, an input temperature profile, input rheological parameters, and then we evolve the model, and then we get the results at different snapshots at different times. A couple of words about how the model looks. We have it is roughly 4,000 kilometers in width and 800 kilometers in depth. And in the zoomed-in plot, you can see the oceanic plate, which is at the center. It is 450 kilometers in width and 50 million years in thermal age. On the left of it, you see the upper plate, which roughly corresponds to the Tisza-Dacia plate, which is coupled when it comes to rheology. And on the right, we have the lower plate, which is interpreted as the Moesian platform, which is decoupled. We have a weak zone marked with black below the upper plate, the back arc extension. And I would like to show you a couple of snapshots of the model evolution I have 6 figures here. In the upper panel, I have the composition plots, so that shows how the different components look at the different snapshots. In the lower panels, I have viscosity plots, where sort of these darker blue colors correspond towards the lower plate. This is not a sort of dynamic push. We prescribe this push to the upper plate to get subduction going, and then we stop the push at 36 million years and leave the system evolve by itself. So in the first part, we have the convergence of the upper plate towards the lower plate, the subduction of the oceanic slab, and after that, we see a collision of the upper plate with the lower plate. We see the slab starts to move into the vertical position or closer to vertical position. So essentially, we see slab rollback. And if you look at the for the third panel, we see the lower viscosities associated with the weak zone. So we see the weak zone activating and the back arc extension.
But practically, your model is producing or creating that image where other people said 150 kilometers, but here reducing at least 200 kilometers in space between where abduction initiated. Is that correct? Yes? Okay,
so if I go back to the setup, so essentially you can see this SWZ triangle. This is essentially the weak zone that initiates the subduction. So I would say that in let's say 2,200 meters, not meters, sorry, kilometers. This is where subduction starts to happen. And if we go here, we are at let's say 1,800 kilometers. So I would say 400. In this model, we have 400 kilometers of difference. But this is the well, maybe in the first order is the question of how wide ocean we put between these continental plates. So this is also a question of geometry, let's say. Okay, thank you.
For the presenters who do not want to have their presentation on a recorded public, such as YouTube, please let us know to remove it from the video. Okay, now, because we are basically Dinu, and he or she will convene the first part of the afternoon session. Irina, the floor is yours.
Thank you. Can you hear me?
Yes, otherwise we'll give you a microphone.
Thank you. We are about to start the session number 3, Geohazard and Hydrogeology. And I would like to welcome the first speaker, Ms. Dorina Țambrea, with the presentation Gas Hydrates, Gas 6 and Gas Escape Features in the Black Sea.
Gas hydrates from offshore Romania. Before of this, when I started to do this presentation, I look at this sentence: a life dedicated to Earth sciences. And I would like to continue that Mr. Dinu has his life dedicated to the students. Because he was like the son, and his students, friends, and colleagues. Most of us wrote the PhD. In the same context, I remember that in 2017, Mr. Dinu sent me and Ioan a letter and asked if we could do a review about the gas hydrates from offshore Romania. We were busy. Ioan used to work with Repsol, and all his time was dedicated to the company. I was involved in a very difficult, but Mr. Dinu let us 1 week, and after that he told, okay, you are busy, but you are not very busy, so you still have some time to do something for this project, and to start to write this review about the gas hydrates from offshore Romania. So we started, we worked, and we published this paper in the Geoecomarina in 2018, and also it was published in Russian language in a book from published by the Academy from Kiev. And now let's start to speak about the subject. Okay, where we are in the western part of Black Sea, where there are a lot of seismic lines acquired both from industry point of view and also like this one in red and in blue, acquired with specific dedication for the gas hydrates and the sedimentological future in that area. I will give you a list about with the people who worked on this subject. It's a bit boring, but I would like to show you that the gas hydrate was studied here in this area starting from 1974 by Ifremora and Zischenko, and then continue in 1999 by Duo-Fernel. In 2003, Egorov analyzed this area and concluded that the distribution of the gas seep, gas flares, and gas hydrates in Black Sea is closely related to the presence of the channel and mud volcanoes. In 2005, Ziemler detected the BSR, bottom simulating reflector. In 2007, summarized that Ludman summarized that the gas hydrates and the free gas accumulation of Romania are characterized by a complex interplay of the lithology, the host sediments, stratigraphic background, and local tectonic pattern. Merey Sinayuk in 2007 did they selected the gas production method of depressurization as the most favorable for the Black Sea gas hydrate, and they did numerical simulation of this type of production. And now I will take step by step, and I will show you a few results of projects that were done in this area. About the distribution of the gas flare, gas seep, and gas chimney in the Romanian Western Black Sea, it is concordance with the geomorphological characteristic of the area. The northern Black Sea, the northern Black Sea, from the Romanian area, it's characterized by a relatively wide shelf. It's between 60 and 200 kilometers, with a shelf break at 120 to 170 meters water depth, and a lot of canyons with large deep sea fan complexes. On the shelf, the highest concentration of the seeps is found in elongated depression above the margin of field channels. On the continental slope, and because in that area there is no pockmarks, there are some seepages along the crest and the sedimentary ridge. On the slope, seepage also appears in the vicinity of the canyons or near the scarp and of submarine landslides. In Popescu and al. Considered that the coastal and shelf break shallow gaze area correspond to the high stand and low stand depot centers. Gas in these areas most likely results from in situ degradation of organic material, and with a small contribution of deep gas in the shelf break accumulation. On the western part, there are Popescu et al. Considered that the gas came from deep area, from the Eocene deposits. They migrated up on the faults, or migration could be related also with the depositional system. Some of them, and they could be observed on the seismic data, with a specific seismic phases characterized by chaotic seismic phases, and they are present on the seismic data like chimney gas. Some of them reach the base of the sea, and some of them remains in the sedimentary data. Besides this, they said that the release, the gas release at the sea floor, it represents at water depth shallower than 725 meters. And they observed on the seismic data acquired in by Ifremer and Joe Comar in 1998 and 2002 that the sweep gas are present where the faults cut the bottom sea. About the glass sphere, Riboulot et al. In 2007, they found out that the continental slope morphology of the Romanian sector of the Black Sea is affected by several canyons. They consider where the imprint of geomorphology and local lithology seem to dictate the location where gas seep occur. They found in this area 1,400 active seeps within the 1,200 square kilometers of the shelf and slope northeast of Danubian Canyon. Most of these seep occur along the canyon flanks, faults, and in association with pock marks and mound. On the on the seismic lines that crossing the area called by Popescu free gas area, they find out that below 20 meters of sediments there is a mass transport complex which is characterized by on seismic phases mute, and below of this there are seismic phases which could be characterized by the presence of gas free on the shelf and on the slope in this area. The gaze could reach the bottom sea, creating this pock mark. The same thing is happened on the line which is located in the area comprising the transition between BSR and free gas area and BSR area of, and also on this seismic line you can see the BSR, the bottom of the hydrate stability zone, the free gas effect with high amplitude, and also the chimney gas, which is the way of migration. Hillman et al. 2 minutes? Okay. So Hillman and al, based on the seismic data, they found that there are a lot of canyons, a lot of slumps, and related to these slumps, there are a lot of flares. Also, they found out that Hillman et al. Found out that there are 3 groups of migration of the gas. first group C is related with these chaotic facies and with the flares. The second is this narrow structure with high amplitude. Here it's better seen on the seismic line, above acoustic blanking underline, which can reach the bottom sea or not. Okay. In 2002, Jan found the BSR, single BSR, and also on another seismic line, a couple of BSR. Here there are 4. This I would like to show you because this I like very much, and even I do not have any time. I will show you because Popescu found that there are 3 areas with the gas hydrates. And in this area, there is something very interesting that below the first BSR, in the channel where there is coarsening material, there are free gas. And you know, the first BSR, so that means the base of the stability hydrates zone, became an anticline, creating the structural anticline, and below the free gas could be accumulated. And on the levees, there are other BSR, and this BSR below of them has high amplitude of the seismic data and also free gas accumulated. And this is the last, okay. And what all the people did in this area and could be summarized something like that, the gas hydrate, the front gas hydrate discovered by Popescu is superposing with the theoretical zone of gas hydrates established by me in 2007, that the gas hydrates from found by Lutman and Popescu are superposing, that the sweeps and chimney gas and flares are located near the channel, near the slums. And they are also in the basin, the area where the chimney gas floor and mud volcanoes are present. Because the gas hydrates is an unconventional resources, maybe in the future they will find a way to produce this type of gas, and for that reason the researches must continue and do not stop in this point. Thank you very much, and apologize for
Unfortunately, there is no time for questions, so we move on to the next speaker, Mr. Cosmin Ghiță, with the presentation Gas Hydrates of
Okay. Hello, everyone. My name is Cosmin Ghiță, Geology and Engineering Shared Services at OMV Petrom. And I'm very honored to present here today to the symposium. Although I never worked with Professor Corneliu Dinu, I'm very happy and blessed to work with some of the the people that he worked. Today I will present a case study regarding the gas hydrates offshore Georgia in terms of geohazards. So, okay. Okay, this is the agenda. I will pass on because I know that we are a little bit late. My objective for this case study was to investigate the presence of gas hydrates and shallow gas accumulation, and also other DHIs in the area of interest here, and at the end to generate a geohazards map in regards with the gas hydrates and shallow gas accumulations. A closer look. The study is located in the eastern Black Sea. Here you can see with the red polygon the area of interest. It's actually also the perimeter of the seismic 3D volume. In terms of regional geology, I will not get into details because this is not the topic of the subject. But we are located in the eastern Black Sea basin. As the regional geology for offshore Georgia, it's split, let's say, in four main parts: the Adjara Trialet folded thrust belt, the Rioni Basin, purely massive granitic body, and the Greater Caucasus Fold and Thrust Belt. The study is located actually on the offshore continuation of the Adjara Trialet Fold and Thrust Belt, which actually has the name of Gurian Fold and Thrust Belt. Here we can see an interpretation done by Gabor Tari and Mike Simmons in 2018. And we have the general structural components, these three big anticlinals, Colchetti, Lasica, Iberia and Lasica. Here you can see them on the seabed map of the area of the interest. You can see their directions. What is important here to observe the big detachment that occurs actually at the base of the MICOP group, and something very good to mention, that the source for the seeps and the shallow gas accumulations that I will show you are actually thermogenic gases from MICOP source rock, Eocene Kuma source rock, and also biogenic gas. These were documented by Dembicki and Thomas Pape in their papers. I will briefly go over. This is the Endor 3D, which is cut. Actually, the data is restricted in depth at minus 2,500 meters or 3 seconds, and the data courtesy it belongs to the State Agency of Oil and Gas, Georgia. Okay. So because the study is focused on the geohazards, the geohazards represent a geological process which can have big impact if they are triggered, and they can be naturally triggered or anthropic. In our case, in this study, we will see what can us as, let's say, explorationists can trigger if we are not assessing the gas hydrates and the shallow gas accumulations prior to drilling. Gas hydrates are considered a crystalline solid, which is actually composed of a gas molecule trapped within a cage of water molecules. Macroscopic, it looks like an ice, and what is very, very important to mention that the gas hydrates can only form in certain temperature and pressure domains. And here for the Black Sea, for the Western Black Sea, it's this interval of -10 to +32 degrees and 2 to 10 megapascals pressure, which was estimated by Mrs. Zambra. And also the depth at which the gas hydrates were identified from -700 to 1,600 meters. In order to interpret the presence of the gas hydrates, we need to understand what is the bottom simulating reflector. The bottom simulating reflector it's a seismic reflector which forms because of the difference of acoustic impedance that forms at the boundary between the gas hydrates bearing interval and the below interval which actually can have gas in it. So if we look at the velocities, we have the water velocity, and then we have a positive amplitude while going into the gas hydrates bearing interval, and then a negative amplitude and reverse of polarity in the shallow gas accumulation. And this is a feature. This is a feature for the BSR. So in order to correctly identify it, we have to look at the polarity of the reflector. Another feature is that it simulates the seabed form, because as I told you, is dependent on temperature and pressure. So it mimics the seabed. And the third feature is that it cross-cuts the layering. So if we are looking here, these reflectors are going, let's say, a little bit inclined, but the BSR, it's cross-cutting them. So this is how the interpretation was performed. Here is a seismic line, actually two of them. Here is the location, uninterpreted and uninterpreted, and you can see a feature seismic reflector which cross-cuts all the stratification, and it's mimicking the seabed. Other important features like gas chimneys, here you can see it, a wipeout zone, that means a zone with poor reflectivity. This is a regional line that crosses the survey and passes through two of the most important mud volcanoes in the area, MV3 and MV1, as I call them. And you have a closer look here, and you see that all of these features, the mud volcanoes, are actually related with some faulting that's happening in the anticlinals. So you will see that there is a trend of the mud volcanoes and the gas hydrates and the shallow gas accumulations to form above the anticlinals. Another feature, which I'll pass quickly, are the pockmarks. Also, and they form at the seabed because of the sediments with high gas content just collapsing. This is the extent of the gas hydrates which I mapped on the seismic. As a, let's say, a QC, we can see that the shape of the BSR horizon, which is the base of the gas hydrates, it's similar with the seabed. So this is a fairly good QC. Then I made an RMS map just below the BSR to to show the shallow gas accumulations below. To have an idea of the mud volcano scale, you have here, for example, Pechiori mud volcano, which has a height of, let's say, 70 to 75 meters, and the diameter between 1.8 to 2.3 kilometers. So they are quite big. This is the tallest one, the Iberia mud volcano. Here you have a sonar view of the seeps that are going into the water. This is also a sonar view, but from side scan. And these are my conclusions with the final map. The presence of the gas hydrates was identified over an area of 477 kilometers. They are considered free gas accumulations below the gas hydrates because they act like a seal. And on the map, you can see that I overlapped the RMS map showing the high amplitudes for the gas accumulation over the seabed map and also the extent of the BSRs. So with red, you have the locations of the biggest shallow gas accumulations, like here also. Mud volcanoes, 6 of them identified, and also pockmarks all around the area. And this map is very important prior to an offshore drilling campaign. So, thank you. Okay, thank you.
So, hello everyone, my name is Cezar Iacob, and after seeing so many deep and very deep studies, today I'm going to take you a little bit back to the surface to talk a bit about some near surface things. So basically we're going to focus on this thing that you see here, horizontal directional drilling. So actually this is a geotechnical study, if it works. Okay, we're gonna just go back like this. So it's a geotechnical study without real geotechnics in it. So it's basically mostly related to geology. So horizontal directional drilling, it's basically a type of drilling that is used to underpass pipelines or cables under obstacles like rivers, protected areas, these infrastructural elements. And it's mostly used in Romania for pipelines like gas pipes and oil pipes. It's used also for water pipes, but currently in Romania nobody invested in this so much. So these are basically very complex engineering projects because the near surface, it's like very unpredictable. And when you underpass a river, obviously the most unpredictable area from geological point of view that you can find, it's in a river valley. So when undercrossing a certain area, these projects basically assume a lot of knowledge. They need a huge amount of knowledge about the geology there. Because first of all, these wells, they have like 1.5 to 3 kilometers length. So They are like really big. And they are horizontal. I mean, they have huge potential to collapse. So another problem with this project is that they need to have big holes. For instance, for the project that we are working on, and we're going to present it now, they need to underpass a pipe of 600 millimeters in diameter. So they need to make a hole of 1 meter in diameter that has to hold there for like 3 weeks until they manage to go 2 times with the drilling column and then pull the pipe from one place to the other. So they need to have a lot of knowledge to mobilize a lot of techniques in the area to hold the hole there. So our project is focused in southeastern part of Romania, and basically it's a part of a bigger pipe that will take gas from the area of Black Sea and connect it to the rest of the internal gas transportation network. And it has 2 crossings here and here for the Danube. Basically, we have the main course of Danube in Gropen area, and in Pecenega, where we are working for the study now, we have a crossing on the branch, Măcin branch is called, belonging to the Danube course. So this is exactly the study area. Basically, we have something like a 1.5 almost kilometer length drill that we need to make. And there is an entry and an exit planned. As you see, we have also some variation of level. So we have almost 40 meters in altitude here, and we're going to go down to like below sea level underneath the Danube. From geological point of view, we are in the eastern part of Romania, eastern part of the museum platform. Is the uplifted part where we can see the basement outcropping. We find here this formation which is called the green schist. It's a very slightly metamorphosed sandstone and argillite. And this is mostly covered with loess formation. Beside the loess formation and the green schist, we also have, as we expected, quaternary deposits associated with Danube. So this is what we expect here. We expected the green schist to find, we expected the loess, and we expected sands and some gravels from Danube. So we made a geological mapping, and we found what we expected before. So this is the green schist outcropping near our study area. It has these loess formation on top of them that on outcrops we found like thicknesses of 4 to 5 meters. But from the general landscape, we assume that the thickness is much bigger. So basically we have green schist giving the main geomorphology, we have the loess covering it, and we have everything here which is recent sediments associated to the Danube. Okay. As something strange is like we had here a plateau, which is like unnormal for the area, and it created some question marks that became true after that. So again, our main formation. So the loess formation, it's a formation with a sub-Aryan depositional genesis, very porous and very dry at the surface. Okay. So we started investigating with wells. We've done quite a lot of geotechnical wells, down to 50 meters. And we found some unexpected things, because we expected to find a lot of green schist there, but actually in a single well we found that green schist. In rest, we found the expected loess formation down to 20 meters, and then a yellowish brownish formation, which was not expected there, and then the sands and the gravel. So we performed a petrographic study on this formation, and basically it appeared like a silty carenitic formation with a lot of carbonates, and with quartz and some other clay minerals. Apparently no fossils, and kind of not unconsolidated plastic. It's not a loess, but with a 40% of porosity. So these data are very important for the drilling process. I will just explain at the end. However, so basically it remained a big question mark what that formation is. Then we went further. We've done a lot of seismic surveys, shallow seismics, with using a hammer and some wireless geophones, so 110 wireless geophones. So we've done a lot of seismic profiles like this. Data processing in this kind of environments for the seismics, it's quite challenging because it's not like the regular seismics. This is exactly what you remove from regular seismics. This is the low velocity layer, so we can't do migration here. We have to constrain the models based on the wells. So we find the reflectors on the seismic sections, and we tie them the wells, modifying the velocities. We have huge lateral variation for velocities, and so basically it's a very stressful process, but in the end it looks nice. So these are tying of the wells with the seismic lines. Then we performed geoelectric surveys, which again were like really interesting. We tried 2D inversion for the geoelectric surveys. It just didn't work out because we have very, very big lateral variation of resistivities. So we went back to the 1D surveys. We found very different electric sounding curves characteristics for the three domains that we had. The part with that formation, and the part with the Danube, and the part with the other side of the Danube. It's easier when I put it like this. And this is where we saw the green schist coming in the geophysics. But what we found here is that the loess, which is normally conductive, here it was like very resistive because it's very, very dry. And the formation beneath, the carbonatic formation, looks very conductive. This basically states that there is a huge difference in physical properties between the two formations. However, in the integrated interpretation, we just put back all the data that we had, and we created a model. These kind of models are what these guys need for building the design of the well. So basically they have to make a path through this so that they would drill as much as possible in friendly formations. Unfriendly formations are these from here. So the gravel is the worst because gravel is unstable, and gravel can cause some very big problems after the well has been done and when they pull the pipe, because gravel can scratch the pipe, and those pipes have around them a coating that is designed to protect the metal from corrosion, because that pipe has to stay there for at least 50 years. And the corrosion action of the water basically destroys the pipe in less than 10 years. And if they pull the pipe and it gets crashed, they will never know. It will get to the surface, and then the beneficiary will make the electric test. If it loses electricity along the line, they will not receive they will not make the reception, and then you have to do it again. And it costs like 20 million, so basically you bankrupt. So basically, the thing is that they can really go in 3D with this. They can go down here, they can go up, they can go up, down, and up again, because they can control very, very well the trajectory of the well. But they have to know with huge precision where they're at. So in this case, all our study showed that the Lăzărescu formation is like very dry and with a 42% porosity, and that will be the end of the drill. However, if they control properly the pressure here, and they get into this formation, which is not sensitive to moisture, in time, it will be cavern as well, because they will have to stay with the water here for 1 month. So if they know that they have sensitive to moisture formation, then they will put a casing from here to here. All this information, basically, they are very important, because when they start drilling, they don't have that casing there. So they have to order it with 2 months ahead. They don't have the proper additives for the mud, because they have to order them, because they don't know exactly what they need. So these kind of studies are like very important with a very, very high stake. So here the error must be 2-3 meters at most. So basically some of the conclusions are like that our formations are like the Lăzărescu, which is dry with high porosity, stiff and sensitive to moisture. This formation, we called it unconsolidated marl. We don't have yet arguments it's a marl, but we have to call it somehow so that they would understand, because if I would just call them, we have a siltic granitic formation with carbonates and some quartz with high porosity deposited in area condition or shallow water condition, they will just ask for translation. So you have to give them something that they know. So we called it unconsolidated marl with a high porosity, but it's carbonatic and with some swelling clays in some areas, but generally it doesn't swell. The green schist, as we saw it, consolidated, fractured. In this case, it's impossible to drill in unconsolidated and consolidated formation, because it's different techniques. So they either drill in consolidated, either in unconsolidated. So they need to know precisely where this is. And the other formations, important is the gravel that they need to go around it. So basically this is, thank you for your attention.
Understand where is the, so basically the green schist at the base, or is green schist above the unconsolidated?
No, this is the green, the base, yes. We expected it to be here, but it's 30 meters lower, or even more, 40 meters lower, and we have a 40-meter thick formation that it lies also underneath the Danube. And we'll have to study more to see what formation that formation is.
Formation, which is the dogger overlying green schist, look like?
Well, I imagine that we should have seen some fossils in this.
No, because it's the case of dogger. It's one of the most important nonconformities. So it's reasonable to have it as fluvial fossil void formation and to compare with your samples.
Well, yeah, for sure it's worth more in detail studies. The limitation here is that this kind of project needs to finish in 60 days from the moment where they give the project. So, but
1 day trip.
Well, when you find out where to go.
The maps, it's under carbonate platform. There are several spots in Serbia over with outcrops of
Yeah, so it will be interesting to see.
I want to ask you, traversing the Danube, which geophysics you use? Seismic in the water?
No. We didn't perform seismic into the water. We only went to reflection seismic here on the shores. We didn't do it in the water.
I'm speaking about the gravel. What is the...
So this is sand. So we have two types of sand, a very fine sand and
The Danube is 200 meters large.
So basically this is interpretation.
It was a white zone on the geophysical map.
Yes.
It's a white zone.
Well, everything between the investigated areas, it's interpretation, but you know, how else?
Entitled Overview of the Dacian Basin Hydrology.
Ca să schimbați slide-urile, apăsați pe ăsta. Ăsta în jos.
Da,
și pointerul celălalt.
Și pointerul
ăsta.
ăsta.
Și microfonul ăsta. Să ne cântați o serenadă.
Da. Okay. My name is Marin Palcu, and I present you an overview of the Dacian Basin Hydrogeology, and the same of this work was dedicated to the Professor Corneliu Dinu, because he worked in this project. Same Irina Dinu do the mathematical modeling of groundwater flow on the lower, and same on this project work my colleague Adrian Iurchievici was participating on this project. So, on this presentation we discuss all the types of the aquifer system and their natural limits, the main aquifer system, system in fissural and karstic rocks from Cretaceous formation, and same we discuss about the aquifer system from the Upper Miocene Sarmatian rocks, and same the Pliocene rock aquifer system, and the aquifer system from the lower quaternary deposit, and same shallow aquifer with the local development. The aquifer system for the first type of the store rocks, the granular aquifers and the fissured karstic aquifers, and from the groundwater storativity we have the unconfined aquifers and confined aquifers on this area, and same from the surface extension, there are the regional aquifers and local aquifers, and after spatial expansion, the one single layer aquifer and the multi-layer aquifer. The discussion of area of the Dacian Basin is a large basin of the southern part of Romania and some of the southeastern part of Romania, this basin. Here the geology of this area, and then there are many type of drilling works. On the blue, there are the hydrogeological research by the hydrogeological wells, production wells, research wells, There are over 5,000 wells, and the same the oil boreholes, many with a black color, and for the boreholes, many boreholes for coal bed research. The hydrogeological map of this area, we have through part of this, the western part of Dacian Basin, and on the eastern part, we have the great hydrostructure of Cândeș-Frătești beds. Now we discuss about the aquifer system in fissured and karstic rocks from Cretaceous limestone. This aquifer has a position on regional extension in the southern part of Mesian platform. The type of porosity is fissured and karstic porosity. The recharge there is from the northern part of Balkan area, and saying the groundwater flow from the south to the north, and some characteristic, the transmissivity is 100 square meters per day. The hydraulic conductivity between 0.2 to 66.2 meters per day, and the discharge of well is comprised between 9 and 75 liters per second. This aquifer is more complex because in the southern part, in Giurgiu area, it's drinking water, but to the north, in the Bucharest area, to the depth of over 2,000 meters, there is a thermal water with a temperature comprised between 50 and 67 degrees in Otopeni area and Balotești area. The next system aquifer, it's upper Miocene rocks. These have same regional extension, but in the northern part of the limit of Carpathian 4 deep, and same in the Getic depression, and site have developed local aquifer in syncline and pericline areas. This extending to the south, groundwater become with great mineralization. The mineralization increased to 50-60 grams per liter, and the groundwater have the characteristic of reservoir waters. Same, the aquifer are generated in the granular rocks and in the carbonated rocks in any area. And the recharge of this aquifer is from Carpathian areas, and general groundwater flow is on direction from the orogenic of Carpathians to the platform area. This is a correlation from the Miocene formation. Here are the aquifer in the Dacian on the lower Miocene, and this on the aquifer, many aquifer in the Romanian formation, and same in Quaternary formation. in detail on the quaternary formation. It's on the base, the lower quaternary aquifer, like Cândești and Frătești beds, and on the upper quaternary formation developed the local aquifers. This is another correlation between, and this is a large area with the aquifer, and the western part, to the west from the Walt River, developed spatial Pliocene aquifers, and in the eastern part was developed the lower quaternary aquifer. It's the largest hydrological structure from Romania. This is, we named this hydrostructure Cândești-Frătești hydrostructure. This is a recharge area for the aquifer formation in eastern part of the world, on the lower quaternary formation, and the blue, it's a discharge area for this aquifer. On the same in the Oltenia for the quaternary formation, it's the discharge area, it's more large, like in the southern part. This is a connection between the river network with the groundwater, because this large hydrostructure was developed on the more river basins, like Jiu, like Olt, Argeș, Danube River, and in the Siret and Prut River. Now we discuss some aspects concerning the aquifer system in Pliocene rocks. These aquifers have a regional extension on the Dacian basin, both in the foredeep area and the platform area, have a variable depths from outcrop in the zone of permeable deposit and over 1,050 meters. The rocks in store are the granular type, fine sand, clay, silts, medium to coarse sands, sometimes gravels. They are largely associated with Pliocene coal deposit in the western part. And same, the stored water has an accentuated quantitative variation from low mineralization water to mineralized water. Concerning groundwater quality, the hydrogeological importance presents the western part of the Dacian basin in Oltenia region, and same on the northern eastern part of the Moldovan platform. The west to the all several aquifer structures are separated on the lower Dacian and same in the three aquifers in the Romanian formations and lower quaternary. The porosity is granular types, and same, the storage is unconfined towards the natural limits and under pressure on most of the territory. Multiply recharge from Carpathians. Some characteristic, the hydraulic characteristic, conductivity hydraulics comprised between 0.1 to 16 meters per day, the transmissivity between 0.4 to 800 meters, square meters per day, same another. This is a hydrogeological map of the aquifer from Pliocene formations. We're not make details, we're passing quickly, and a cross section from this aquifer in base the regional aquifer on the Voltania. These are artesian aquifer. Same, this is hydraulic transfer of groundwater from the orogenic area of the limestone, the Carpathians. This transfer, the hydraulic transfer in the Miocene formation, and after that, this hydraulic transfer is in the Pliocene formation and then in the Miocene formations. This is a potentiometric map for the artesian aquifer. On the blue area, the aquifer is artesian. This is for western part, and then we're passing for the lower quaternary system. This is a large aquifer. We're passing this in the depression, jetic depression area, and in the platform. And same is a schematic. This is the coal bed and the thickness of this hydrostructure. And the same, we present you the groundwater flow. This is a recharge, the recharge area, and the discharge area, as in the groundwater flow. And this is the flow under stress. We can remark in Bucharest area a large depression due to the water wells supply. There is over 3,000 for groundwater supply. Thank you.
If there are any questions, or if not, we can have a question on having coffee.
Okay, we start again at 50-50. 50-50. Yes? 25 minutes. Nice coffee. You will wake up for questions.
Okay, we start.
Welcome to everybody to the last session of this special meeting dedicated to our professor, our colleague, and especially our friend, Professor Corneliu Dinu. We start this session. We would like to be in time because the time is very tight. Our keeper, Liviu, is very strict on this respect. So the first presentation will be done by our colleague Csaba Krishek. It's about filling of sedimentary basin and the burst of large rivers, the Lower Danube network in the Dacian Basin, Romania. Csaba, please.
Thank you, Marius. Good afternoon, everyone. That's me in the Danube Delta, trying to get to Sulina. It was very, very hot, and we had a really long way to go. So, started from my sort of Danube Delta experiences. With my colleague Cornel, started to think about, okay, that's the Danube Delta, that's fine, but then how it gets there. So, I mean, it starts, if we look at the course of the Danube, basically, as we see, it crosses several basins. So it starts in the Alpine Molas Basin, goes through the Vienna Basin, that's basically a part of the Pannonian Basin, really, and then goes across the Iron Gates, gets into the Dacian Basin, and goes into the Black Sea. Now the question is how it gets there, and I think there are basically two different hypotheses. One is that all these basins are filled to spill. So I'm the Danube, I'm getting on this basin, I'm filling the Pannonian Basin, then filling the Dacian Basin, and I get to the Black Sea. That's hypothesis one. And the second is, this is not the case. That's the so-called concurrent basin fill model, where I fill up these basins with local systems. And when the sediment supply exceeds the accommodation space, then these river streams, they combine together into one large river, which we call the Danube. So what we know about this is, if we look a bit on the stratigraphy, and that's for the Pannonian Basin, Dacian Basin, and the Black Sea Basin, as you can see, even for the bird's eye view, a very simplified diagram, the stratigraphy is quite similar. There are some obvious events which you see across the basins. Now, the Hungarian colleagues, and that's the work of Magyar et al., they mapped out nicely how they call the proto-Danube fills up the Pannonian Basin, prograding from this part at 10 million years, and then gets to the Iron Gates sometimes at 4 million years. So age-wise, basically, this is in the Pontian, Maeotian, and sometimes in the Eastern Parathetic scale by the Dacian gets to the Iron Gates. If we look on the other side of the system, the storyline is not so clear. So in the Black Sea, when actually gets the Danube, that's a big question mark, still debated by many people. It has been dated at 4.3 million years by Arian et al., but they say that that's the oldest probably entry age, can be also younger than that one. Then some others, including ourselves and Yunus, we said that, oh, look, I mean, there is a big prograding sequence, clinoforms in the Black Sea. And what we see, there is a major changes submarine fan architecture in the Black Sea, going from a sandy system to a more muddy system. Even more important, if you map out this unconformity actually at the shelf, that fits to the intradacian major sea level fall. Then we said that, well, most likely a very muddy system ends up in the Black Sea, which must be the Danube, and hence the entry of the Danube into Black Sea could be in the intradacian phase, which is pretty much the same time when the Danube gets at the Iron Gates. However, interestingly, we still know that there are marine transgressions evident in the Eastern Dacian basin. It has been mapped by a number of authors, and by Marius, for example, the forams in the Eastern Dacian basin, which are younger than this entry point. And also some other colleagues, Matoska et al., they claim that in the Galat Seaway, where we should see the Danube crossing into the Black Sea, that is really quaternary, the first sediments which they see. So depending on who you ask, basically, it can be as early as in the Dacian, but it can be as young in the quaternary. So we said, okay, let's try to see what's going on in the Dacian basin. Maybe we got smarter how we got the Danube from the Pannonian basin across the Dacian basin into the Black Sea. We mapped out the Dacian basin architecture on seismic data correlated to wells. And there are a number of horizons we mapped out and constructed regional sections, and based on this horizon made a number of thickness maps. I don't want to go into details, too much details in it. You see, for the example, this is the Badenian Sarmatian thickness maps, where you can nicely see some of these depot centers are controlled by these strike slip faults on the basement. And then later on, in the Meocean, we start to see some prograding system going from north to south, and also some others filling up that part of the basin. Interestingly, the Eastern Dacian basin seems to be filled much quicker than the western part of the Dacian basin, and later on, because of the Fokshan subsidence, the depot centers are again shifted more into the Fokshan area. So, if you want to summarize this one in some cartoons, we see in the Sarmatian, north of the Trotuș fault, we have these Sarmatian clinoforms, which are actually this system which is coming from the north. Then in the mid-Meocean, there is a major low stand into the basin when this part of the basin is filled. And then this is the most long-lived feature in the basin. As you can see in the Pontian, we start to see clinoforms coming from very different directions. And then by the Dacian, really the Dacian basin is filled. So what is left may be a less than 150 meter shallow basin. So then the first evidence of the Danube, what we see, actually is this part of the seismic when already the basin has been filled. And if we look at the western part, this is how it looks like. So that's a thickness map based on these delta fronts of early Dacian age, where you see the thicknesses are increasing toward the iron gates, where you expect the Danube step into the basin. And later on, basically, you see these large quarries with meandering fluvial belts. That's the coal measures of the Western Dacian basin, which interestingly, if you map out these paleoflow directions, some of these channels, they were flowing further to the north, basically going along the Carpathian foredeep. So this is the first evidence what we see in the basin. If I go back to this one, so what is happening that the Danube probably steps in the Dacian basin, which is already filled by that time, goes quickly and meets the other system which is coming from the north, and only when the accommodation space is less over here, probably can step the basin really into the Black Sea, which is most likely happening very young in the Quaternary. All right, so coming back to my first question, do we think that is a fill and spill model? The answer is no. And we rather think that is actually, in order to form a continental scale river like Danube, in going across very different sedimentary basins with different tectonics, you really need to fill up first the basins, and then in later on you can coalesce the systems to form one single and large river system. Now the question is that how this refers to the global database. And that's a map with the large rivers of the world, which we put together with Cornell. And over here you see a characterization of the rivers. So in one side we see we plotted the discharge area, going larger in this way. So the biggest ones are, for example, in the Amazon over here. And on this graded shade is indicating the complexity of the basin itself. So going 1 to 5, we have basins we have rivers which are flowing across more and complex basins. And our conclusion is really that there are only a few rivers which are flowing across several different basins. And more importantly, the Danube really stands out as a river which connects the most complex basins, several complex basins on this path flow. And I think this is really possible because we have a fragile system where the sedimentation overrides the accommodation supply different basins, and this is how it emerged the Danube. Thank you very much.
Thank you very much, Csaba, for this very nice talk. If there are any questions or comments, Liviu.
I have two questions. First of all, because the Danube is a high complexity system, I mean, the first question is, can you really apply the principle of muddy discharge to be the one of a major river system, the Danube? Because it's a highly complex system. Can you really apply that principle? I don't think so. I mean, you cannot compare in terms of complexity the Danube with the Ganges. Okay.
That's correct. In a way, that's correct. But if you just look at how many basins flow across the Ganges, basically the foreland of the Himalayas, versus the Danube, the Danube, in fact, is more complex because that's just a 4D basin which ends up in the Brahmaputra Delta. I do think if you look at the discharge of the Danube, I think it's muddy. You don't get too much sand into that system, and if you classify them with any sort of submarine fan systems, you would classify them as a moderate system.
Black Sea with all the straps, it will be muddy anyway.
Yes, I think yes.
The second question which I have is depends what you call the Danube, okay? I mean, I fully agree with you that the Danube in its modern form has been established, as you say. But you cannot deny the fill and spill, because we know that fill and spill events occur. This is proved by paleontology.
So what we call Danube is the present-day Danube, how it looks like. It gets from the Bavarian molars and gets into that one. So the present-day river.
The present-day Danube it's not even the present-day Danube was not where you put it, because you prove very nicely a migration to the south of the Danube.
That's correct.
After. So what I'm saying is that the basin is still events, they do exist in the moments of high stands. I mean, and you proved that with your work in Transylvania and the Pannonian Basin, this is proved. And how do you call it, the work of Marius also proved that in terms of paleogeographic evolution. So moments of basin fill and spill, they do exist.
We never said in the paper, in the talk, that it doesn't exist. We just say that the Danube formed after this basin has been filled. There are moments in time where basins can be connected, that's fine, but that was not the case for the Danube.
This is what I wanted to hear.
Thank you.
More time for questions, huh? Students have questions.
Like in 1 minute.
Okay.
Yes, we get a good monkey way for the good question. Question after graduate.
No, before. Students have priority.
After experience.
So, I would like to present our next speaker in this part of the symposium, which is Professor Marius Stoica. And apparently he keeps us in the same Dacian Vasile. Marius?
Thank you. Thank you, Marius, also. It's funny to be introduced by my former best student in micropaleontology. Marius Tirița, I introduce you also now. Actually, it's the first time after 2 years that, personally, I can talk face-to-face with people. I think it's a good opportunity to meet the scientific community, and I think that I am happy that this happened with this meeting in the honor of Professor Dinu, which was our professor, our friend, mainly our friend. A short story about Dacian Basin. I have many slides, but I will pass very fast because I have many cartoons and so on. Of course, it's not only my work, it's a team behind. It's a team that most of the name that you see here, and also still there is place to add more names, former students that work in the Dacian Basin in the last almost 20 years. The Parathetis, very nice name in the last time, Mega Lake Parathetis by Palcu, 2021. Just a second. Yeah. This one. What is Parathetis? Parathetis, it was a large sea. Used to be, we talk about Parathetis since the boundary between Eocene and Oligocene, almost 34 million ago. And the Parathetis formed due to the tectonical collision between Asian plate, Indian plate. And then the former Tethys Ocean just was spread between Mediterranean domain in the south and the sister sea of the Mediterranean that was named Parathetis. Very nice name, also the lost sea, the lost sea of the Eurasia. In fact, the name Parathetis was first used by Russian geologist Lăzărescu in 1924. But in that time, Lăzărescu actually was professor in Odessa, and then he moved to Belgrade. Lăzărescu referred to Parathetis only to Miocene Sea that started in the Miocene from Rhone up to recent Caspian Basin. But we know already that Parathetis is a bit older, not only from Miocene. It's generated in the late Eocene, close to Oligocene. And if you look to the paleogeographic map, the Parathetis was quite big in the beginning, from Rhone, let's say Paleo-Rhone Basin, up to Tarim Basin. If we look at the map, there are almost 6,000 kilometers. It was quite an important sea. Maybe the same size or even bigger than Mediterranean Sea in that time. But once it was formed, the Parathetis already start to have problems to retreat because the ongoing tectonic and uplifting area around down that the Parathetis start to retreat first from west and also from surrounding areas. Traditionally, for the late Miocene time up to now, the Parathetis is used to be shared in central Parathetis with Vienna Basin, Pannonian Basin, Transylvanian Basin is a satellite also of Pannonian Basin, and eastern Parathetis with Euxinic Basin, Caspian Basin, and what we are talking now, Dacian Basin. Actually, the Parathetis was a playground for many geologists in the last 20 years, especially people that work under, let's say, umbrella of Utrecht team, a Dutch team. And we spent almost 20 years checking different basins along the Parathetis. You see here Wout Kruijsman, Cor Langerijns, and most of them are former PhD students from Utrecht and from different countries. To be honest, the first initiative belonged to Professor Dinu and Professor Sirkrering. When in 2002, they come in Romania and they started to set up the collaboration in the Carpathian area in the frame of Netherlands Research Center for Integrated Solid Earth Science, ISIS. And then Professor Kruting came together with young collaborator in the time, yes, Liviu Matsenko, Giovanni Bertotti, Wout Kreischmann. Here it's Professor Wout Korlangeres, was not that young in the time, and they started the program. So I was introduced in this program in the time, actually. Dacian basin sediments are staying on. We can find the Dacian basin deposit are superposed on two important tectonic units. I mean, Carpathian foredip and Moesian, and also part of Moldavian platform. In our study on the Dacian basin, actually, we studied quite a lot of important sections. You can see several sections. All of sections are in the outcropping area. And in fact, we investigate marginal part of the basin, which somewhat it's important because studying marginal section, you can see every change of water level. They are much more sensitive to water level changes than the deeper basin. This is just an example. There are very long sections, actually, sometimes kilometers of sediments we have to map in detail. When we say detail, it's every meter we map with samples from paleomagnetic point of view, for paleontological point of view, and also sedimentological informations. In my case, I was focused on biostratigraphy, because in this case, ostracods, because they can give you very important information about time control, I mean, relative biostratigraphy, relative time, about water level evolution, water level, and about salinity and other environmental. Of course, the Dacian basin history is pretty long, and I will not keep you for all history. I will focus only on one moment, I mean the Messinian, and not all Messinian, a part of the Messinian, when, the Mediterranean experienced dramatical events. Some people believe that in that time, Mediterranean almost completely desiccated. Some people believe that not real desiccated, just lowering the level a little bit. As you can know already, there are different chronostratigraphical schemes from the Mediterranean and from Dacian basin and from Parathetis. This is because we use fossil, but fossil in Mediterranean are marine fossils. In the Parathetis, they become to be brackish or freshwater fossils, so we cannot compare apple with pear. So we have different regional stages in Eastern Parathetis. But if we need to compare the Messinian, then we have to look in the Dacian basin to the top of Meotian and the Pontian time. And I will bring you fast to this short story. In the late Meotian, what we have in the late Meotian, according with sedimentary structure, with fossils, apparently we have only freshwater fossils in the late Meotian, and from sedimentological point of view, we have several cycles of from deltas deposit with coursering up deposit, and you already can notice that the water was pretty shallow. We see wave ripples very often in upper Meotian. So we can conclude, this is cartoon that Liviu used to laugh a little bit about my cartoons, but they are very simple. We could consider, according with fossil, with sedimentary structure, that in the late Meotian, the sedimentary was quite proximal. So, if we, also a cartoon, the situation in the late Meotian was, in my opinion, in our opinion, like this. This is Dacian basin, no connection with the Pannon Lake, possible weak connection with the Black Sea, and of course, no connection with Mediterranean Sea. Also, you can see into a sort of paleogeographic map. Let's go a bit ahead, and it's an important moment now. It's a Meotian-Pontian boundary. Already something changed. We have a flooding event at this level. The freshwater fauna was completely replaced by more salty fauna. I think they leave you or name her like this. Me? Okay, sorry. And this is this level. You see the resolution of sampling on the, in this case, Lănicu de Buzău Valley. We found a level with forams, which is quite unusual because forams disappear for a long time from the Asian basin, but we still have forams there. So we have this level with forams at the boundary between Meotian and Pontian. And suddenly after this level with forams, we start the Pontian with an anoxic event here, and then the real Pontian mollusk. This is the most famous actor of between forams because this is planktonic Streptochilus. We went a little bit away in Taman Peninsula, now in Russia. It's impossible to go now there. And what you see on the North Black Sea, on very nice cliffs there actually, we see the same boundary with the same forams, with the same Congeria novorosica, and then anoxic event, and then start the Pontian, real Pontian fauna. Go a little bit ahead to far away, another 1,000 kilometers in Azerbaijan, the same, we notice the same story. I'll pass fast about this. So we have evidence for this event. Time control is important. Everywhere where we found this level, we've done magnetostratigraphy. And all the time this level is to be found on the top of this normal paleomagnetic crown. And that we calculated is 6.1 million years, this level with foraminifera, which is important because for more than 2,000 kilometers we have a very high resolution stratigraphic marker. Why it's important? Because before there are many correlation of Meotian Pontian boundary from almost 9 million years to 5 million years. So we cannot work with this because it's impossible. There are some differences or some. Okay, I'll finish soon. So we found this level. That means that we can level a little bit the stratigraphy. It's important. So we have a massive event in Eastern Parathetis, a massive flooding. Is dated 6.1 million years because we have this level with forams that can correlate for more than 2,000 kilometers. This event is followed by an anoxic event in deeper part of basin. It's normal if you mix salty waters with fresh water, we create stratification, like it's in the Black Sea today. But the basin will recover after thousands of years. Which is also important because the water level rose. We reconnect the Pannonian Basin with the Dacian Basin, and Pannonian endemic fauna migrate in Eastern Parathetis, creating so named Ponto-Caspian fauna. Where the flooding is coming from, we don't know yet. Possible Mediterranean, possible Indian Ocean. Indian Ocean, it's all ideas have strong and weak arguments. I am the adept and possible the only one of Indian Ocean. So we have at the Meotian Pontian boundary, this was the situation in the late Meotian. Then we have a flooding that covered almost everything, reconnect also the Sinoa Lake, reconnect possible with the Mediterranean. We have this level with forams. Going a little bit faster, in the lower Pontian, it was a good time for fossils. We have fine grain sediment with mollusk fauna from Sinoa Lake. You can see, I skip this, also very nice ostracods. So, upper Pontian, it was a period of high stand. Something like this. Going to Middle Pontian change, okay. Come on, you've been my student. The Middle Pontian, it's a period, again a bad period for the Dacian basin because the water level drop. It's like someone took the cork from the basin and water level just suddenly dropped down. Again, we have this kind of proximal facies. We already see ripple marks. It was coal intercalation, roots, also freshwater fossils. And yeah, we pass from fine grain to much more coarser sediments. I mean, we pass from high stand to low stand, but no more, the water drop no more than 100 meters. Possibly it's equivalent of Lago Mare. So we have this event in the Mid Lithospheric. Okay, I'll skip this one. We go to Upper Pontian. To Upper Pontian, something happened in the basin. We have a sharp transition from the Mid Lithospheric to Upper Pontian. Again, from coarse sediment to fine sediment. You can see very nice here. It's like, it's very clear that something changed in the basin. Again, we have a Pannonian mollusk in the basin. So we pass from low stand again to high stand. This is also on the Slanic Valley. I will pass fast on the slides. On the Slanic Valley also can see very nice this change of the. This is my friend Wout Krijnsman, famous in the Mediterranean stratigraphy. So this can be Meotian, Pontian, Middle Pontian, Upper Pontian. That means Messinian, Zanclean boundary. Could be at 5.3. Okay. So I have this situation here. It's a flooding. So in the conclusion, we told this story to our students, and this is also related to Professor Dinu. All the time we try to explain to students drawing on the paper the evolution of the fauna, of the lithology. When we finish the paper, we start to draw on the stone to make sort of lithoglyphs. I try to make them very simple. High stand, lower stand, high stand. Professor Dinu all the time understood this. Some other geologists was a little bit skeptical, but they try themselves to understand. So this is the conclusion, the evolution of the Dacian basin written on the stone. Upper Meotian, low stand, flooding, lower Pontian, high stand, water level drop in Middle Pontian, again, flooding, and Upper Pontian, again, yeah. Sorry for long, but Professor Dinu, I've been many times on the field with him. It's a remarkable professor. He explained so nice tectonic, and he put all the times in the tectonic frame. He was all the time around young students. I think that even Dan Jipa was his PhD student in the end. And to be fair, Professor Dinu told me that his first love in science was paleontology. I think that he was the best paleontologist between tectonicians. Thank you very much. Sorry for so long.
Otherwise, we would like just a quick comment. I was not your student. You? No.
No, I had only good students. Sorry for joke, but I actually, Professor Dinu really like jokes. Okay.
So we'd like to invite the next speaker in the session, which is Eugen Tudor. Eugen, please.
Se vedeți? Merge și așa. E ok? Da, e ok. Hello everyone, I'm Eugen Tudor, I'm a geologist with Untitled, and I'm also a former PhD student from Professor Dinu. He was actually the one I started my PhD with. So today I'm going to be talking about a small part of my PhD thesis, focusing on the foreland basin, Eastern Carpathians. So we're talking about a large basin. It's not a complete foreland, only on the eastern side, and the stratigraphy is mostly we're talking about ages starting from Badenian to Romanian to recent. Of course, the foreland basin as a fill existed prior to Badenian times, but most of it was captured within the thin-skinned thrust belt. So the actual basin is part of Parathetis, as Professor Stoica talked about recently. It was largely influenced by connections with other basins. We see marine deposition, Badenian to Sarmatian times. Also, as the basin was shelving upwards, it becomes more lacustrine, and eventually it becomes continental. Well, another thing what we see is that the thickness variability per age segment varies in time and space. And as expected, the largest subsidence is actually where the Carpathians bend, where the South Carpathians transition to the East Carpathians. And also another thing that we recognize is that the transition from an underfill stage to an overfill stage occurs somewhere towards the end of the Sarmatian. Another important aspect of the foreland basin evolution would be what happened before the basin, actually. So this is a subcrop map at the pre-tertiary unconformity, showing you the geology behind the tertiary fill. So one important aspect would be that the north orogen basically is prolonging into under the Carpathians, and it behaves as a large indenter. Basically, as the Carpathians evolved, exhumed, and moved towards the east, it hit this large indenter. It was affected by it. And major lineaments also played an important role, how the basin evolved, how it developed in space, and how the sedimentary facies evolved through time. Now, there are several pre-existing basins. We're talking about East Mesia, North Dobroja, Bârlat Basin, and also the Moldavian platform. These three basins, basically, they began somewhere in the Paleozoic, and they have very similar stratigraphy. It actually, one of the most important observations would be that there is a lot of erosion related with the North Dobroja orogen, and on its flanks, basically, we have more erosion in the Bârlat, but we see similar facies. So there was connectivity in the basins during the Paleozoic and Mesozoic times, and basically everything became connected in the tertiary. And as I mentioned before, the actual foreland fill began way before the Badenian, right? So we recognized a lot of facies specific to foreland in ages related to Lower Miocene and Oligo-Eocene. Let's see. There are existing models, and one of the main observations would be related with this fill of the Focșani Basin, which is an anomalous fill. Basically, we're talking about a large depot center where large subsidence was recognized, and it was treated as a focus of sediment fill. And what was recognized in time was that the Carpathians rose sequentially, right? So it wasn't a one uplift moment, and each of these moments in time affected the sedimentary fill, basically creating space for the sediment to be deposited in. I had a chance to look at several data, mostly subsurface, looking at seismic profiles, some well section correlations from the northern to the southern part. And one of the main observations would be that basically the quality of data plays a huge role in how we envision the geological model, right? Because we only have available in most of the basin vintage 2D seismic, which was acquired prior to 1990s, and there are sparse 2D data sets. Also, the well data was highly dependent on basically the industry, and because of the amount of discovery, which is less in the eastern part, in the Moldovan platform and in the foreland, we don't see as much of high density of well penetrations as we see in the south and in the southwest. And this affected the way we correlate things. Also, the way the topography, the present day topography cut the geology, that also is important. And the quality of data in the wells is also very important. Most of them are vintage wells, only have SPN resistivities, very few cores, and makes it very, very difficult to recognize sedimentary facies, as you would see in a modern well with complex data, with complex cores. And the tie of the well with the seismic is very poor, because they didn't commonly acquire velocity information in the wells, so tying the wells with the seismic is poor. So we begin with that. Our large recommendation would be that once you have 3D surveys large enough and complex data in the new wells, you can tie them together and you can make a really nice stratigraphic model. Well, because of the industry, we don't have that, but maybe in the future. Now, based on the field, this is basically a reconstruction of some of the facies we see in the wells, and these are reversed. This is the middle Badenian facies specific for this area. So we're talking about evaporites with shales and sometimes some sandstones. And what happens is basically we're in a restrictive environment. The middle Badenian is trapped somewhere within this area, and you don't find it further to the south. The upper Badenian, it becomes a more marine basin, a more open sea, and it starts flooding the pre-existing topography, and so we start seeing more and more Badenian covering the topography. And also, one important aspect, we start seeing carbonate production. So this carbonate production that it is basically a ramp, we see some reefs, they represent the edge of the foredeep. Post-Badenian, we transition into the lower Sarmatian. Actually, most of the Badenian, one main observation is that it's found further to the north of us, or within the Carpathians. So most of what we see in terms of thicknesses is quite reduced. We're talking about a few hundred meters of Badenian, right? So when you look next to the front edge, when you see thickness it's so thin, it actually makes you wonder why wouldn't you see thicker deposits closer to the Carpathians? Well, this is mostly related with how the Carpathians rose, and that happened after these depositions. So we also see that post-Badenian, basically the progradation of the clastics enters the basins. We see clinoforms filling the basin, and this is what we call the lower Sarmatian. The lower Sarmatian on the fringe develops a large carbonate platform, and we see that a lot of clastic sandstones are trapped in the topsets. Further into the Sarmatian, everything progrades further south. We create a new depot center, and this is synchronous with the last moment of tectonic exhumation. So you start having large topography, you have what to shed, and your system delivers the sediment into the basin. At the end of the Sarmatian, that's why I was saying that we're transitioning from the underfill to an overfill. Basically, there's a large unconformity affecting the Sarmatian. You're eroding a lot of the upper Sarmatian. Basically, you're cutting it out from any connection with the basin. And we transition to a Meocean basin, where the Meocean, again, sheds sediment from the uplifted Carpathians, but also from the uplifted orogen. The North Dobroja orogen acts as a source of sediment for the Meocean. So we start seeing clinoforms prograding east to west into the basin. And we actually starting seeing the Meocean depot center shifting. So if you would go here, then you have a lot of shale in Meocean, not a lot of sand. And here you see a lot of clinoforms, rivers, and deltas. And basically the North Dobroja orogen, and helped by these active faults, it started shedding sin. And it basically traps the sediment on this side. And it's a shallow basin because we don't see a lot of deep water sediment, only maybe pro-delta turbidites. Further on into the Pontian and Dacian and Romanian, basically this represents only part of what happens. In the Pontian, we would go in this area, we would find a lot of continental to fluvial to maybe some shallow marine deposits. as we move into the basin, we start seeing this type of confined turbidites. This is part of the lower portion, and basically the basin becomes shallower and shallower. It's the flooding event that you talked with, the upper portion being very muddy. And then the last stages, we see basically the basin being overfilled. We don't see any more marine or lacustrine deposits, but a lot of fluvial and alluvial sediment. And this is a cross-section north to south along the frontal thrust. And it's showing you a lot of formation. And this is showing the high density of possible clinoforms with, in the outcrops, you would find the topsets with a fluvio-deltaic, but in the deep, you would find a lot of confined channels, even some turbidites. And actually, the transition between Badenian and Sarmatian might be a large unconformity. But it's mud on mud, so it's very difficult to map. In the eastern Moesia area, where if you have a north-south section, basically what we see is the Meotian system. We see very, very sandy Meotian. We see this lower portion, clastic system. It's marked by that sea level drop that was talked previously. And the Sarmatian itself is quite muddy. Very few sand is preserved within it. And we actually see some blind trusts in the area. In the north, in the seismic, clinoforms, a lot of, basically each event represents a clastic influx into the basin. Now, when we look at the geometry of the basin, we recognize that in the north, you don't see the deep foredeep that you see in the southern area. And that might be because most of it is trapped within the thrust belt or is below the thrusts. So what we see here in terms of foredeep depths might be just an elongation within below the subthrust, which is very hard to image. And in the eastern part of Moesia, once we build a chronostratigraphic chart, we see that there's a lot of sediment trapped in palotopography, palovalleys. We see a large muddy system in the Sarmatian, and basically seeing the shallowing upward system with continental to shallow marine to lacustrine, Meotian to Pontian. And then if we look on the eastern side, basically there's a lot of foreland geometry that we don't see anymore because it's already in the thrust belt. But what we can recognize is that there are pulses of sediment, basically forced regressions followed by transgressions. Basically, the transgressions represent a period of estuarines, fill, maybe some saline basins with sapka. And we see that there is what we might consider a formal bulge. And this has been also showed in published material by Ari and Deleuve with the reef belts migrating eastwards. So the basin extends further from our country, right, in Moldova, in Ukraine. And in Moldova, at the edge of Moldova, you can see there are Sarmatian carbonates. And everything is shallowing upwards. And I think that's it. Yes. So the basin got filled from north to south, most of it. We recognize there are clastic pulses associated with tectonic uplifts. There is a bulge migration that can be seen during Badenian and Sarmatian time, not so much afterwards. And there's a larger part of the foreland stratigraphy that is captured within the fold and thrust belt. And we see that there is a transition from an underfilled basin to an overfilled basin somewhere at the end of Sarmatian. An important aspect is that we see a lot of carbonate production during Badenian and lower Sarmatian, not so much afterwards. And the fact that poor data quality really limits us to have a more conclusive model. Thank you.
Just a quick question. I saw a reference to Dorothea 2021. Is this published?
Part of it. It's only the subcrop part with the PNU.
Where is this published?
Geoeco Marine, I think.
Okay,
yeah.
thank you.
Then we pass to the next talk of our colleague, Peruroban. It's about the provenance of oligogenetic and quartz ionites at Apex.
Thank you for the invitation. I'm honored to be here at this symposium dedicated to our Professor Dinu. And I have to mention that Professor Dinu, during his PhD study, studied Cretaceous deposits in East Carpathians, also my target. But today, I will talk about the provenance of Oligocene, lithic, and quartz arenites in the East Carpathians. Two formations very famous here in Romania, Cliva and Fusaro formation. Everybody knows provenance, Cliva from east and Fusaro from the west, the inner part of Carpathians. But we want to understand the sedimentary routing on compressional margins of the basin. Why Cliva? Sorry. Why Cliva and Fusaro and the Oligocene? Here in the thin skin nape of East Carpathians, the outer part of the East Carpathians, this large yellow part, Tarkov nape, contain this formation. They are very, very different from a lithological point of view. Fusaro, it's lithic, and Cliva, it's quartzose. This means they are very easier to recognize on the field, and also there is a data set available at the moment with the adjacent units around the Carpathians basin. That means Dacia block. There is a database of detrital zircon ages, and also a database with zircons from Craton, European Craton, Museum platform, North Dobruja, and Balkan area. That could be a very useful tool for provenance analysis. So the target is to reconstruct the sedimentary drainage system and understand the sedimentary style. And we define that during Oligocene there already was a foreland basin, sensu Peter Dissel. A very, very short description of the evolution of the East Carpathians. Everybody knows from this hall that the East Carpathians was the subject of the Middle Jurassic extension, creating Chahlau-Severin Ocean. It's not clear what amount of oceanic crustal crust was produced during this extension, but we know that starting with Lower Cretaceous, from Cretaceous onward, start the compressional stage with a progressive shortening, creating the modern fold and thrust belt structure in the Carpathians. Here is a table, stratigraphical chart with the names, the main tectonic units in Carpathians, thick skin nape here, Dacia, Jetic napes, and then the sedimentary fill of the basin, Moldavian basin, thin-skinned napes. Baremian-Aptian is the starting of subduction, but the Eocene record an important uplift here. It's a sketch after very, very recent paper, Nature, that suggests an uplift and a change in the exhumation style in the Carpathians. And supposing that it's a moment of consummation of oceanic crust and this compressional stage of the basin. Which is important for our topic is that this thicker skin nape was already exhumated and uplifted during the Oligocene time, our target here. And also could be on the evolution of the basin could be a real foreland basin at that time. A detail here with the stratigraphy. This is after previous works of stratigrapher or tectonics in Romania, but upgraded with our work. This is Fusaro and the interfingering area with the Lower Cliva Formation sandstone, made by sandstone. The other main target is to compare our data, detrital zircon data, with the available data from the adjacent unique, and we have to do a short description here. And the red area, it's Dacia block, Bucovinic, and the Jetic napes. The shape of the zircons look like this one, with a high peak of Ordovician peak at 460 million years production of zircons, which looks similar with the South Carpathians, the same shape, Ordovician production of zircons. Very, very different from North Dobroja and the Danubian unit, which is considered the margin of the Musean platform, that shows this high peak of 600 million years Cadomian zircons here in the North Dobroja, and also in the South Carpathians, the same shape. Actually, North Dobroja look very, very similar with Danubian unit, except these ages exceeding 1 billion years. Yeah, a lot of very, very old zircons in North Dobroja. Also, there is a database available from the work of Balintoni, and in the basement of the Musean platform, exposed in here in the central Dobroja, that look like North Dobroja, with this peak at 600 million years, and some older zircons. And also this data on East European Cratone with the age exceeding 1 billion years. These graphics have been improved, but I've chosen for this presentation the data from Ducea and their collaborators. So, we have done with Mihaela Melint some analysis on nanofossils, calcareous nanofossil, to establish the ages of depositional age. We have done sedimentary facies analysis, petrology, and detrital zircon geochronology. This is a nice section here exposed across the Buzău River. This is Fusaru South, Cliva South, and interfingering area. We find that the top of Fusaru formation belong to Lower Agvitanian and one biozone, and also this depositional age is proved by detrital zircons, the younger zircon that we have found in this section. And we documented here the interfingering area, the Vinețișu location. We have seen, you can see the Lower Cliva formation, which is covered by Fusaru formation, but in this section there are some quartzose level of sand, similar with the Lower Cliva formation. This is very important task here. From a sedimentary point of view, we have done some detailed section in the north and the south, each locality of study, and we found some common elements between the two formations: the presence of the low and the Bauma sequences, an expression of a high density and the low density turbidite currents. And this means channel fill, frontal, splace, levee, typical for a turbidite system. Okay, this is some different elements. Fusaru is full of conglomeratic facies, the is poorly sorted, some grain shales intercalation, and some transitional flows between cohesive and dense turbidite have been documented by Sylvester. And also paleocurrents, we have measured some paleocurrents, are orientated to the east and the northeast. Cliva look somehow different. Very, very few conglomeratic levels. A good sorting of the sandstone, bituminous shales between chelons, levee, some slumps and injectites, but paleocurrents are orientated to the west and the northwest. From petrographical point of view, Fusaru is rich in the clayey matrix, has a lot of lithoclast, metamorphic, similar to Dacia basement, some sedimentary, carbonatics, and very interesting volcanics, and so volcanic shard. Very, very well preserved. That means could be very, very young, probably Oligocene in age. Instead, Cliva look very clean quartz. That's why it's a good reservoir for a hydrocarbon. It's blue, its porosity, rich in quartz, exceeding 90% of quartz. Many sections have been counted, point counting, which was very challenging and sometimes boring for us. But we do this, and projecting these famous tectofacies Dickinson diagrams with yellow and blue, it's Cliva sandstone. Cliva sandstone with blue from the interfingering zone, and with orange and red, it's Fusaro sandstone, red in the interfingering zone. That proved that the provenance of the Cliva sandstone, it's cratonic, interior cratonic, but for Fusaro, it's a recycled orogen. And plotting in this diagram, quartz monocrystalline lithic plus quartz polycrystalline, we make a differentiation between Cliva, cratonic, and maybe quartzose recycle. Probably the polycrystalline quartz come from the eastern quartzose recycle orogen. I have read that on the TTZ zone, Mazur provides some trusting and reinterpretation of this area. Probably could be a secondary source for a Cliva. And transitional recycle and lithic recycle for Fusaro. But with which recycle orogen, we think that this could be Chahlau nape and or even Teleasian nape that could be exposed and supply sediments into the basin at that time. And probably the most important slide, it's this one. We have done for samples from each locality, and we have found that Fusaro, the first two in the upper part of the graphic, look very, very similar, with a peak at 460 million years. That means it's a Dacia provenance here. And also we saw the signal of the 72 million years ago, it's a banatitic volcanism, and 21, 22, 23, they peak it at 25. Somehow it's a Oligocene volcanism. And very interesting is this peak at 300 million years ago, found in the north and in the south. Probably was reworked by from the Audia nape. We have met this peak in the previous our work in the Cretaceous deposit. Probably the Audia nape have already incorporated in the orogenic wedge. Instead, Cliva look very, very different with older ages exceeding 1 billion years. That means cratonic provenance, or maybe North Dobroja or Miocene basement, but also only in the southern part, in the Buzău Valley, we have met this peak. Is missing in the northern part of the Cliva. And probably this is North Dobroja orogen input. We don't know about Balkan. We don't know about Balkan area. And now only a few slides and I will finish. Some discussion about the provenance and sedimentary route. This is a tectonic reconstruction, a very recent Van Hinsbergen. We have used this one in order to create a paleogeographical map on this tectonical framework. And our paleocurrents measurement and the Fusaro and the Cliva and the previous paleocurrents measured by JIPA. And this is the front line of the Dacia block, and our reconstruction is in between 30 and 20 million years ago. Actually, this is the reconstruction. We have defined here two sedimentary main system. Cliva depositional with a yellow and a cross section. This, with mention, this could be improved, of course. On the eastern side of the foreland basin, the margin was influenced by four bulge here, which supply probably the green schist in the basin. Cliva quartz rich sand transported by long river system. This is not an entire a map. Draining the East European craton was reworked and deposited here in the four deep, most probably during the low stands here. And probably was on the back bulge took place temporary repository sediment. On the western side here, the uplift and the eastward advancing of a thin skin nape here, the suprajetic, Chahlow, and probably most already incorporated the oligomycin orogenic wedge and Audia, and most probably Macla. Provide poorly sorted clastic material here in the basin. Fusaroclastic material was transported via short high energy routing system into the four deep interfingering here. This is area of the interfingering and overlapping the distal part of the Cliva system. And okay, and a south, please. Okay, this is a south input, probably from the western part of the Balkans, to explain the presence of these Carboniferous and Permian zircons, and also Danubian. And probably the bottom current could be reworked and mixed sediment in the middle of the basin. And the conclusions. Our findings, the top of Cliva formation is Shatian, while the top of Fusaro is Aquitanian, proved by also by zircons, two different depositional systems, Fusaro with Dacia, main source, short drainage, high energy, long life, hyperpycnal flow, feeding turbiditic fans, Cliva system, 4-lane units, main sources, long drainage, short life, hypopycnal flow, temporary storage on the shelf, and basin water sedimentation, and the common southern sediment proof by Museum platform, Carboniferous Permian magmatic intrusion within North Dobroja, Danubian, and possible Balkan origin. Thank you. Thank you.
Thank you. I think that we move next to the next talk already. The next presentation is done by Dr. Schleiter. Thermal control of Black Sea basin.
Поразмощите Windows ăsta. Okay, thank you, Marius. To begin, I would like to thank the organizers for inviting me here to celebrate the memory of Professor Dinu, to which I was a student of him on my PhD research together with Professor Kluting here. And today I would like to take you to an area dear to Professor Dinu, which is the Black Sea and the Black Sea Basin. And to make the long story short, I'd like to discuss a bit the thermal controls on the Western Black Sea shelf. And to go. And to begin, I would like to acknowledge a few people here, which are like Professor Aurelian Neguț, to which we're grateful for providing us a lot of information from the wells from the Black Sea, to which he was a part of the research in the early in the late 70s, early 80s, and I'd like to acknowledge Dr. Laszlo Lenke from ELTE in Budapest for his methodology and discussions related to computation of thermal conductivities of the rocks. And to start over, this is a heat flow map of the Black Sea built with International Heat Flow Commission data, which more or less the data are covering the Black Sea basin. But if we are looking to the shelf of Romania, there is not much here. I mean, there is nothing there except this well here, which is Olympijska 400, published by the Ukrainian geologists, and together with Ioan, and later we brought Victor Barbour as well in our team. We decided that it's time to build to update the heat flow map on the Romanian shelf. Just to continue, in 2002, Professor Veliciu came up with a heat flow map built. No, it's working. Built on partly on a multitude of heat flow points around the area, on onshore and offshore as well, and the results of the map would be this one. But except that contour map that was published in the Bucharest Geoscience Forum volume, no data related to temperatures or thermal conductivities were published, and therefore we have to divert a bit to the evolution of the Western Black Sea, where we know that the main extensional period was in the early Cretaceous, followed later by in the Upper Cretaceous and Tertiary by just passive margin and some thermal subsidence. Here on the left we have one of the let's say iconic sections across the Black Sea shelf, built by Professor Dinu in his paper from 2005. So knowing that our main extensional period in the Black Sea is early Cretaceous, and assuming this is the geometry and the stratigraphic geometry of the area, in which basically we have more or less a Cretaceous basement, which is filled up with later tertiary sediments like Oligocene and Poncian and Dacian Quaternary. And then we go further to a better map of Professor Veliciu, published by Dr. Dorina Tambra in his PhD thesis from 2007. And I would like you to pay a bit attention of the colors in this area here. So we have here this quite reddish area, along with this another reddish area here near Mangalia. And if we are looking to the color map here, we are seeing heat flow values around higher than 85 milliwatts per square meter. And as everybody knows, those heat flow values surface heat flow values are quite high. Usually those are encountered in the highly extensive areas, like the Pannonian Basin of our colleagues from from Hungary, or for the instance here in the southern Aegean Basin, where we know that we have a quite serious stretching of the lithosphere on the whole ensemble. Yeah, and then together with Ivan and Victor, we had the question why Professor Veliciu used those. What he did to compute those high values of heat flow here here on the Black Sea shelf, despite that our area was stretched in the early Cretaceous, long time ago, more than 200 million years, and also is filled with recent and cold sediments. So to us, those values of 80 and 90 milliwatts wouldn't make sense to the current configuration. And then we went further. We spent quite a lot of time on finding and classifying all the piece of research that was carried out in Romania or abroad. As a starter in this database, we used what was existing in the faculty here in Bucharest from the late 70s, early 80s, when Professor Dinu and the other professors like Teodor Neagu or Professor Dragastan, Professor Grădinaru, they were working, and Professor Neguț here on the petrophysics chair, they work on the Black Sea exploration. Another source of inspiration for us were a lot of PhD theses carried out on the Black Sea shelf, from which we managed to extract a lot of important information regarding the lithology of the area or area of interest. Also, another source of inspiration were conferences and papers. Some of them are here that provided us a lot of information, and I prefer to stay out on the original research papers, because probably all feel like 10 slides with just 2 papers published on the matter here. So to compute the heat flow in the area, we need basically, according to the Fourier equation, we need just 2 important things. One is the thermal conductivity of the rocks, and the second is the thermal gradient of the section where we are computing the heat flow. So, because after our investigation, we couldn't find any thermal conductivities produced in the laboratory, we decided that we should start to compute some synthetic thermal conductivities, starting from the basic, from the typical thermal conductivities for the sandstones, shales, and limestones, which were taken from the Schlumberger Petromod library. And right here we have the whole summary of what we managed to compute. This is the synthetic thermal conductivities for each stratigraphic intervals that we considered in our wells. And also here we have some volumetric heat productions taken from the paper of Professor Dumitrescu from 2007, in which he deals with the other part of the Moesian platform, the one on close to the Foxian Basin. for later, for a bit of modeling, we considered as well his thermal conductivities and volumetric heat productions that he used in his modeling, because it was the closest analog we could have. Here are some parallel of other thermal conductivities that were computed by other authors in the area, and more or less, and not going too deep into the, we are basically on the same page. Regarding the temperature gradients, we use what was published by Dr. Radu Olaru in 2018, where in his paper he pointed that there are two types of thermal gradients for the Romanian shelf. The cold one, which overlaps usually the slope, the wells drilled on the slope of the Black Sea, and the hot one, a warmer one, I would say, that overlaps wells which are towards the inner shelf and the shoreline. And using this stuff, we came up with this map, in which we integrated the whole data set existing on the International Heat Flow Commission with what we computed here. And probably you would ask why we got this high heat flow value there. That one is the Vadu well, which, as you probably my Romanian colleagues knows, that is a Upper Jurassic depth here, and the salt usually has a special behavior regarding the heat flow. Thank you. Otherwise, we are, I mean, in terms of heat flow, we are not, there is nothing special there. We are around the 50 milliwatts per square meter. And to test our map, Ioan, after a lot of negotiations, he built this crustal cross-section that starts here in southern Bulgaria, in the Kamcha depression, and goes north here to Danube Delta. And here we have the upper cluster configuration with and the lower cluster crust configuration taken from Tesauro et al. 2007 from the EU Crust 07 model. And after Ioan built this cross section, we put it in a finite element modeling software, and we tried to see and by solving the heat diffusion equation, we tried to see what's the result of the modeling. And on the first case, we assumed that the base of the lithosphere is around 100 kilometers, and here on the upper part we have the heat flow response measured right here at the top of the section. And as you can see, we are not very different than our model. The average would be 64 milliwatts per square meter. And then we built another model with a lithosphere base at 120 kilometers, and we got a lower response of an average of 55 milliwatts. And as a final let's say best fit model, that we assume a variable base of the lithosphere with a 150 kilometers thickness and 100 kilometer thickness in the north. This is in the south, and we got an average of 55 milliwatts. And these are a bit of conclusions. what I told you. Yeah, they are preliminary because we still have to test a lot of things on the modeling. It's not that simple. So basically, the average surface heat flow is around the 50 milliwatts, the uncorrected one. And if we would like to apply the correction as suggested by Ericsson in the 1970s, this would jump to 58. And in terms of modeling, as you can see here, we have the jiggle lines are the model, the response of the model, while the blue line here is extracted from the heat flow map along the cross section. And as let's say for strong preliminary conclusion to get this to match the calculated curve, not the modeled one, we need at least a lithosphere of 100 kilometers or more. But we still have to run a lot of things in the near future to finish our modeling. Yeah, well, thank you. If you have questions.
Thank you, Marius. Time for question.
Thanks, Marius, for this presentation. How big is the sediment latency effect here? For this model, let's say with a big lateral variation in lithosphere thickness, do we expect any contribution by lateral heat transfers?
Usually in this kind of modeling, you run just a simple model, steady state model here. The lateral heat transport is not very taken into account. We're just going for the vertical heat flow. We still was steady state. We still have to come up with evaluation for transient effects. But as I say, there Ericsson, which was one of the students that was participating in the IODP wells in the Black Sea, he said that a 50% correction is needed for the shallow sediments, which is not much. The things are worse in the middle of the basin, where we have like 30, 40 milliwatts uncorrected, but even if we're applying this correction, it's still very low for extensional basin. Thank you very much.
Okay, we move to the last talk for this session. It's Istvan Gheorghi and Sandra Pasos, exploring in the fold and thrust belt, the Eastern Cordillera in Colombia, perspectives.
Thank you.
Por favor, señor.
No merge bine. Stai pointerul. Nu, l-am.
Invers, stai în jos. Asta e următorul slide.
So, ladies and gentlemen, good afternoon. It is my pleasure to be here in Bucharest. I've been absent for a long while, but Liviu Matsenko invited me to participate, and I gladly said yes because several reasons. I'm a native of these lands, grew up in the other side of the Carpathians. Number two, I have a big respect towards Professor Corneliu Dinu. I met him 30 years ago, like I met Professor Kluting. I met at that time Liviu Matsenko. This happened at the first ACAPA meeting in Graz, if you still remember. Okay. So that time I was supervised by the much regretted Frank Horvath, who passed away prematurely, and obviously it is another big loss for our community in this part of the world. I tried to stay away from the Carpathian Pannonian issue because I didn't do too much since we published in 1999 our paper with László Csontos and András Nagymarosi, which we did on the Botiza Klippen belt. And I did some seismic work in Hungary, but you know, being outside, I was reading publications, so I didn't lost connection. But it is not the moment yet to jump in. So right now I work as consultant for the oil industry and oil and gas industry. And I'm also visiting lecturer at the Utrecht University teaching seismic interpretation. And so today I will take you to a journey into South America, where I've been working for a number of years, and co-author of the presentation is Sandra Passos, with whom we were working in Bogota for a number of years. So I would like to tell you that I was really fortunate to work in the oil patch, because that took me to interesting places, and the red dots are the fold and thrust belt projects which I was involved in, and beside the technical parts of these projects, I met lots of people, very good technical guys and big friends. And so I don't want to enumerate every single one, but you know, Canada, and then coming back, sorry that dot shouldn't be here because this is the Permian Basin and has nothing to do with fault belts. And Guatemala and Belize, so the Maya Mountains and Chiapas, the Andean fault belt and northern Venezuela, and all the alpine system here, Atlas. Then we moved to Kurdistan, and here is Pakistan, Tajikistan, and so on and so forth, going down to PNG. So what I wanted to say that I have seen lots of fault and thrust belts, and I was trying to pick for you today the most interesting one. I have to thank to these people and companies. So my former employer, Jay Namson. Jay Namson is a structural geologist. He was the first PhD student of John Suppe. And so he contributed a lot to Suppe's work in cross-section balancing, writing the first codes, and so on and so forth. He's retired these days. He doesn't want to work anymore. He's living in sunny California, sipping good wine over there. And Fernando Marcano is a Venezuelan geochemist. CGL was a company who acquired the data for us. GeoStudios is a company who did the surface mapping, and thrust belt imaging is the company who processed the seismic data for us. Okay, I don't want to go through. It is a normal outline showing the area, stratigraphy, geodynamics. The 3D seismic work itself was preceded by a regional study and a basin modeling study, so structural balancing and basin modeling study, and then we picked up two areas where 3D has been acquired, and so the three components of a good seismic program: acquisition, processing, and interpretation, ACPRINT, an acronym, and finally we will conclude. Okay, so here we go. Northern part of South America. This is Lake Maracaibo here, so Venezuela, very famous place. Lots of oil has been found there. And here are the Eastern Cordillera, which is the easternmost branch of the Andes, which is coming up from Patagonia till here. And here it's not bifurcating, but trifurcating, because this is the Central Cordillera, and here goes somewhere the Western Cordillera. And this is the area of interest, so highlighted in blue. And so you can see that practically we are sitting on the top of the Andes. And just to give you a grasp of what we were doing here, so that is about 7 meter high, that tree, and this is where we were acquiring seismic data. Rapidly, just to show the seismic coverage, oops, now works. Seismic coverage of Colombia and the well data. So you see that this part where we were initiating this project is in an area where less activity has been carried out. And here are the stratigraphy and petroleum systems of the Eastern Cordillera. I won't go into details, but it is the classical one, extensional or scenery phase, going from upper Jurassic till, let's say, to this point, then passive infill, and here we start at this moment to move upwards the first compressional moment, and from that one, so we have several big phases, as in the case of the Carpathians, for example. And sorry, I missed to show you, so two source rock intervals and several reservoirs and seals. So it's a multiple petroleum system. And to give you an idea about the complexity of the area, so this is a cross section which was constructed by Bernard Coletta and co-authors. Actually, Bernard used to be my professor in structural geology at IFP school. He's an excellent mentor. Unfortunately, he's retired now, and he's no longer active. So this is a cross section going from the central part of the Cordillera, and this is the Llanos Basin, which is the foreland basin. And what is important here, that you can see that according to their interpretation, the formation goes along basement-involved structures, so a so-called thick-skin tectonics. On the contrary, here we have the work of Covey and Dengo, and they were so nearly the same section, and you see the opposite, so ramp-flat structures, basement-detached thin-skin tectonics. And as usually, the truth is always somewhere in between. This is the most recent by Saylor and others. And here goes the full reconstruction of the area. And so what was important for us, that this Soapaga fault has been exhumed by somewhere Eocene times, because our area of interest is below the Soapaga fault, so in this position. And what we initiated a big project here before shooting the 3D seismic data. So we constructed 6 regional cross line in the area from existing 2D data. The data has been reprocessed. And also important to mention that the stimulus to do this study was because the area has lots of hydrocarbon indications at the surface, so the black points or
what are those? These are the surface indications. The big question is that how much has been preserved, because the whole Cordillera is moving upward, so preservation is a big issue. And I will show you now one section out from the 6, which is this one, all are 3. And here is the section, here is a little gap. And obviously, this is dangerous to do, but we had no other choice. We had good surface geology here, so I'm confident that even if we made several mistakes, is not so big. And so this is the this is a seismic section, has been depth converted. And then, together with Jay Namson, we did the balancing study. So when we had all this, so the surface structural, so the 6 regional lines, along all the 6 lines, surface geology has been also mapped. For reservoir, for seal, and source rock capacity, so every single regional line had its surface information. And after that, it was Fernando Marcano who did the source rock maturity modeling. And without going into details, if you remember, I mentioned that we have 2 source rocks, and here is Fomeke is the older one, and Chipake is the upper one. And based on all the information we had, then we went to design the 3D survey. So 2 areas has been picked, 200 and 230 square kilometer. And here I have to make a parenthesis, because here are several messages for any Foden thrust belt explorer. And number 1, this is a very expensive thing. We have to talk about money, because money plays an essential role. So altogether for the two surveys, we paid $40 million, 40. And it was preceded by a 6-7 month long debate and field. We went out on the field, we tested several sources, we tested shot holes. We made everything, or we tried to eliminate all the risk factors to be sure that money won't be thrown out on the window. If somebody doesn't have the right amount of money to acquire 3D, then please don't do it. You should shoot then a good dense 2D network, because anyways we are looking for bigger or medium-sized fishes, not small things. So take your time and you make sure that you have the money to do this. Okay. Okay, so here is the area. I'm just showing one of the 2 3Ds. And take a look at here is an elevation map. So it is across this line, AB, there is a difference of 750 meters. Anybody who acquired seismic data, 1 minute? 1. Give me 2, please. Should know that this is really a very, very difficult task, and here goes. The 2 3Ds were acquired for a period of 14 months. And here is the seismic data. The first seismic contractor who processed the data for us, you can see that it is not bad at all. And here is a seismic contractor 2. So the same data, 2 different processing sequences applied. So message number 2, do parallel processing with your data. If you already put in 40 million, then don't be short on processing. one single seismic processing is one opinion. You should have at least two. And okay, I skip this one because it's, and the 3D PSTM volume cross line here. Obviously we went from time to depth domain, so you can see what is doing the PSDM. This is much better, and this is not important. And here we have the flow, 3D PSTM volume, 3D PSDM volumes. We interpret both of them, and we want to see the prospects both in time, in depth domain. If they are there and exist, then we are happy. If PSTM, PSDM prospects, they don't match in position, in size, and in depth, then there is a problem. And I don't want to go in every single, because I already mentioned to you what are the messages here. And please allow me 2 more slides. So this is in the Himalayas, in the Sikkim Himalayas in northern India, and this is a seismic base station. This is a passive seismic base station, but we have here 2 active source sections, the Himalayan geotraverses, and this is the data. Take a look. We are down at 22 seconds, so it is quite an effort. And here is the interpretation. It is complex. It is a hell of a complex world, but it is still doable here. So my final message is that, especially here in the Carpathians, please try to shoot good seismic data because it's possible. The only limitation is money, and the rest is blue sky. Thank you.
In the case of your Colombia project, has there been a follow-up in terms of drilling? And how has that been successful?
Sorry. Yeah, good question. And this is one of the reasons that I can't leave with you, because this is an active project. Pacific Rubiales, the company I worked with that time, went bankrupt. And not because of me. But today, this is a license of a company called Frontera Energy. And after many years of silence because of the pandemics, green pandemics, and everything, so they are going to drill a couple of prospects, hopefully next year, first quarter.
Yeah, because we are the last conveners, before to pass the microphone, not yet, wait, to organizer, I would like to thanks to organizer actually for this initiative. Yeah, Ionuț, our younger colleague, Liviu, and help, of course, by Marian, Mr. Mircea Radulian, Dr. Panin, and of course many others. It was a very nice event, and I'm sure that without pandemic problems, they would organize even before this, before the pandemic. And only a few words, not too many. I spent the last 20 years close to Mr. Dinu. He was my professor, but first he was my friend in the end. And my career was very much influenced by him. If it's to characterize Professor Dinu, beside a huge academic, professional personality, he was a very good manager. He was our dean for many years. In that time, the faculty done very well, a lot of collaboration, international collaboration. But beside this, he had a very, very special quality. He never kept for himself. He used to share everything, from professional, scientific, information, even material stuff, even drinks. He used to share with us, with students, with colleagues. If there is a word to characterize Professor Dinu in my mind, it's generosity. This is. Thank you to all being here, but I will pass the microphone to Liviu for the last.
Well, Marius, you don't get to have the last word, so you will have it. I have a couple of practical announcements. So basically, I mean, we've seen today very nice contributions, very nice papers, very nice, research. Some of it does not appear to be published. So you have the invitations from Professor Panin to, let's say, to organize a special volume in the local journal, in Geo-Eco Marina, and also you can always can use the, let's say, the two journals of the Romanian Academy. But besides this, we showed you at the beginning that, I mean, I showed in my presentation that there is still a global and planetary change special issue running, where the deadline is no later than 1st of July. So plenty of opportunities to publish your nice research. So we welcome you to this nice research. And before Ionuț has the last word, there is, I mean, we have to end the session with you. Ionuț will end the session. I just have a small announcement. What do you say about the restaurant? Okay, so basically there is nothing more organized from this moment. The only thing what we did, we booked a number of places in the restaurant called Vatra, which is next to the Cismogenic Park. Okay, so whomever is paid individually, so we don't have any budget, so it. I'm not working with oil companies like you. I'm sorry, but so there is no financing to this conference. Everything we have seen is organized voluntarily by Ionuț, and his students that we have to applaud now, because that is a big contribution of students. The entire teams of students which have contributed to our nice organization. So whomever wants to come, paid individually, we will go to this restaurant. We have a number of places reserved in restaurant Vatra, which is next to the Cismogenic Park, starting 7 o'clock, 7 p.m. 15 minutes walking, 10 minutes probably, yeah.
Depends how fast you are. So, fast and furious. Okay, guys, so, so we end up at this session, or we end up at this symposium. It was an idea to do it since a long time. Unfortunately, we never managed to do it, and online, honestly, was not an option. So we grabbed it and we did it very fast and furious. However, I'm still very happy that we see all of you here. We see different generation, a different mix, both in presentation, both in people which are here. So now this mixed, no, it's very nice, and I'm very happy to see. And there are a lot of surprises coming. And to be honest, we're going to continue different symposiums, like one in October. As Liviu mentioned already, we have more publicity to do it, but we're going to have another one, which is the ILP Task Force in October. That's another story. Now, thanks to you all, we still have a little bit of minutes if you like. There's still some coffee and some cookies left, so if you want to be more sweet. And if you have any problem with sugar, that's it. But anyhow, thanks to you, and I want to thank also personally to Valentin, Nistor, and Vladene, because they actually really carry a lot of things, this one. And the ladies from the office nearby, the secretaries which did all the coffee and all the stuff, they really help. And a good symposium, it's also based on people which do basic things. And that's why I'm really grateful to them. I'm really grateful to all you. I'm really grateful to all of you which come and present, all of you which come and assist, and I'll be very more grateful if in the next meetings, whatever we have, whatever we're going to organize, either in faculty, either in international, either in the Romanian Geological Society, whatever, I would like to see you there. I'll be very happy. So thanks to you, thanks to all, and it's grateful to organize this thing in memoriam of our professor. So, thanks. And also, sorry, last but not least, I would really like to appreciate Mircea's effort here to transmit this one live, this session live. And you see we have a DJ here, so thanks, Mircea. Okay.